They stopped the music, so it must be time to talk. Good morning, everybody. Welcome to the Wednesday morning keynotes. I'm Mark Carlson. I chair the agenda committee for this conference where we put together all the great content you're hearing about. We do have some upcoming events you want to put on your calendar. We do have an annual meeting of the members when we announce the election results. We also have a symposium right back here at the Hyatt again next year. And as part of that, we'll have the Persistent Memory Summit, which you don't want to miss. And we'll have a lot more room for you this year. We also have another couple of SDCs. SDC EMEA will happen at the end of January in Tel Aviv. And also we have an SDC in India, in Bangalore, late May. So go check those out. Registration may not be available yet, but put it on your calendars. And of course, thanks to our sponsors for making this possible. Without our sponsors, we wouldn't be able to put this conference on, so really appreciate that from them. So this morning we're all in this room, and then we have lunch from 12 to 1. It'll be out here in the mezzanine as well. We have breakout sessions this afternoon you don't want to miss. We also have a networking reception this evening from 5 to 7, and then some more exciting BOFs in the evening. So a full day, as usual, packed with stuff. I heard there's some people that still haven't downloaded the mobile app. I can't believe it. It's so easy. Just point your phone right at this little square of pixels here. And you can also log into it to get even more functionality, such setting up your own schedule there and interacting with other attendees as well. And of course, thank you to the SNIA SMB Plug Fest underwriters and participants. This is always an exciting time to get these folks in here, even though they're not speaking, at least they're participating here in SDC. So this morning after me, we've got Dave Eggleston talking about thinking fast and slow. And then we've got Amber Huffman, who's going to talk about solid-state data center transformation. After the break, we'll have a special sort of next generation interconnects. First we'll hear from the OpenCAPI folks, then we'll hear from the Gen Z folks, and then I think Tom is going to lead a Q&A, joint Q&A session there right before lunch. And then these are our BOFs this evening. There's one on desktop applications and persistent memory. There's an open source BOF, and there's a data compression BOF. So that looks all really interesting. So we do ask that you fill out the speaker evaluations. This is one of the ways we shape the content is based on your feedback. So if a speaker gets a low score, we might not invite them back. If they get a high score, we're like twisting their arms, right? So you get a chance every time you go in to speak one of the sessions and evaluate it. So, you know, for each slot, you could be having another chance to win the card. In fact, Dieter Schnabel, are you around? All right, Dieter, congratulations. You won the $100 gift card. So please go to the registration desk and pick that up. So have a great SDC, folks. All right, I want to introduce our next speaker, Dave Eggleston. He's a principal at the Intuitive Cognition Consulting. Dave is the owner and principal. His extensive background in Flash, MRAM, RRAM, and storage is built on 30-plus years of industry experience serving as VP of Embedded Memory at Global Foundries. also CEO of RRAM, pioneer startup Unity Semiconductor, Director of Flash Systems Engineering at Micron, NVM Product Engineering Manager at SanDisk, and NVM Engineer at AMD. He holds a BSEE from Duke University, a MSEE degree from Santa Clara University, and 25 plus NVM-related granted patents. Thank you, Dave. Hey, Michael, can you get his slides up? There's only one. Thanks.
Thank you very much. Technical support. Well, good morning, and I see several familiar faces, but lots of faces that I don't recognize. So I think that makes it a good mix for this conference. And I'm going to talk about today, we're going to start actually with your brain. And so we're going to explore your brain just a little bit. And I know that may sound dangerous, especially at 9 o'clock in the morning. It may not be quite up and running yet, but that's what we're going to do here in just a minute. And I have a very specific reason for exploring your brain and how it operates. So let's jump into it. So here's some of the key points I want to make today. First of all, that the brain can be modeled as two systems. How many of you already believe me that your brain has two independent systems? Absolutely 100% believe me. Okay, two basic systems. Okay, I only saw a couple hands go up, so let's see a little bit later this morning if you agree with me. So as we move ahead into the artificial intelligence era, you know, we have two really key tools in memory to make that happen, and that's DRAM and NAND. And I like to say the future of NAND is NAND. The future of DRAM is DRAM. And I stole that from somebody about 10 years ago. And it's still true today. But there are alternatives that are coming, and we're going to talk about how those emerging memories can be used to solve some of these limitations that we have with DRAM and NAND. So if you're at Micron or Toshiba or Samsung or Hynix, don't worry. You know, your technologies aren't going away overnight. And all of us that are designing memory or storage systems around that, we don't have to throw out that knowledge, but we do have to learn about the new technology. So we're going to talk about that. And then the key point here is that emerging memory, as it gets commercialized, helps accelerate this movement into the AI era. So when S.W. Wirth asked me to talk, he said, I asked him over the phone, I said, well, what do you want me to talk about? And he says, anything you want. And I thought, well, that's really dangerous. It could be anything. But this is a book I'm working my way through. And how many of you read this book? Okay, only a couple hands. I really highly recommend it to you. And I'm just going to give you a tiny little taste of why I do that. This is a gentleman who is a professor. He's a professor of psychology, yet he's done this work very scientifically over decades of time. And what it describes is that we do have these two systems in our brain, and they really help us in how we think and make decisions. So a lot of the book, which we're not going to go into here, but is actually how our brain works and biases our decision making. So these two systems, the one is a very fast, intuitive system. It takes no effort. The other is more deliberative, reasoning, etc. All right, you ready for a quiz? I know it's 9 in the morning and you're going, gee, I didn't, do I have to use a number 2 pencil? I wasn't ready for a quiz. I didn't study last night, but here we go. I'm going to show you 2 images. Don't say anything, just I'm going to show those 2 images and then we'll talk about what happened. Okay, what happened in your brain? You saw 2 images come up. We're We're going to go into this. And by the way, this is exactly the example that he uses in the book to lead off. You saw this image on the left-hand side, and immediately, what did your brain do? What are some things you thought about? What's her emotion? She's angry. You know, who is this person? You might have said, that's my wife, my sister, somebody here I met yesterday at the conference that wasn't very happy with me. You know, you came to a bunch of conclusions immediately. You probably even might have assumed, what are her next words? Not very positive, right? You have a model in your brain. As soon as you saw that image, you called up that model. And you had certain assumptions about it. Now, maybe true, maybe not. But you were automatically geared, without any effort, to have certain information. You retrieved that information immediately. How about on the right-hand side? How many of you solved that problem right away? Okay, a handful of you math nerds probably did. It turns out that we can hold like two-digit numbers. If I came back a couple of minutes from now and asked you what problem was I asking you to solve, you'd remember those numbers. But you parked it. You recognized it as an equation, but you said, I can come back later and solve it. So the system on the left is your intuition system. It actually uses associative memory. And there's models built in your associative memory that you had instant recall. The one on the right, you parked it and you gave an interrupt to your reasoning system to say, do I have to solve that now? If I have to solve that now, I know I can go do it, but I'll kind of do that offline. I'll do that in the background. I'll park that and come back. So these are the way our two systems interact. The intuition system is immediate. The reasoning system is interrupt-driven. It gets called by the intuition system and says, what do I need to do with that information? Now, what are some more attributes about these two systems? So in the case of the intuition system, like I said, it's lightning fast. It happened right away. How many of you did it take effort to recall that model? I bet none of you took effort to immediately have a response there. So it's real time, and it's approximate. You didn't know who that woman was, but again, you might have assigned it to somebody you know in your life, etc. Now, how about the reasoning system? Oh, I'm sorry, intuition, if we think about where that happens for compute, that happens on the edge. And this is as we push compute towards the edge, this is one of the things we want to have there. How about the reasoning system? The reasoning system is slow, it's deliberative, it's very precise. In other words, you could give an answer, you could multiply 17 times 24 and give a very precise answer, but it takes effort. And actually, science shows that when we invoke our reasoning system, we burn power. Our blood pressure goes up, our attention goes down. Think about it, when you're concentrating on solving a problem and applying effort to it, you miss things around you. There's actually, they talk about in the book that there's a very famous experiment where they say, watch these basketball players and tell me how many times they pass the ball. And so if you're concentrating on counting the number of times that pass the ball, you miss in the background somebody in a gorilla suit comes by and waves their arms. How can that be? You're focusing on counting. Your reasoning system is taking over and consumes all that power. So this reasoning system is what we have in our data centers, and it's what we have traditionally for compute. Okay, let me see how many of you now believe that you have at least two systems in your brain. Okay, a few more hands, so I convinced some of you. So again, this is just a little bit of taste from that book, but I, again, highly recommend you read it. Now let's go on. We're going to spend most of our time talking about the reasoning system in the data center because that's something you can go build today with the components you have today. But we will come back and talk about the intuition system at the edge. So if you recognize this guy, Dr. von Neumann, he gave us an architecture a long time ago for our reasoning system. It works really well. It works really well. What do we have for the intuition system? Well, there is a guy that's pretty similar, and his name is Dr. Moda. And he's from IBM. And maybe someday we'll talk about Dr. Moda the way we talk about Dr. von Neumann. And Dr. Moda, and this is literally the mapping of a monkey brain. No, they have not dissected human beings to map the network in the brain, live human beings, to map the network in the brain at this point. But one of the things he teaches is the architecture that we've used for reasoning systems is not the architecture to be used for intuition. So someday we may talk about him in the same sentence or the same way, but we're going to store him. So if you're a load and store person, we're going to store him for now, and we'll come back later and talk about him. But let's go into the reasoning system because we want to talk about the memory tools we have today and the ones we have tomorrow. So as we look at that von Neumann architecture, there's that memory unit. And a long, long time ago, we had HDD and we had DRAM. We were pretty happy with that. But then this thing called NAND got invented. And so we replaced it. And for a while, we're happy with this situation. But there's some problems. So let's go in and talk about what are some of those problems in our von Neumann architecture with DRAM and NAND. So my friends at Rambus, this actually comes from Gary Bronner, if you happen to know him. He's presented it a couple times. And what he does show is the ASP, the selling price for DRAM and NAND. There's an old axiom that memory declines cost-wise at 30% per year. And if you map that out, that actually goes back many decades. However, we see a big problem here on DRAM, and DRAM is flattening out. So its rate of change, now ASP and cost are not the same, that is true, but the rate of change in DRAM has really slowed over the last decade. So there are scaling limits, fundamental scaling limits for DRAM, the way we've known DRAM, that are causing its costs and subsequently its price to flatten out. Conversely, NAND is continuing along pretty much that historic curve of 30% per year. So NAND's doing pretty well on pricing, but bottom line is DRAM costs too much. And a friend of mine, Mark Webb, who's another consultant that speaks, he has a great quote on that. He says, well, and 0 of the DRAM manufacturers are concerned about this. They love it. They're making lots of money right now. And if you're a customer, you're not too happy about that. Okay, so let's go on and talk about NAND. This is a look back at 2015. Again, I stole this one from Mark Webb. He had this nice talk at Flash Memory Summit this year. What about latency? Well, what we see is there's a continuum of latency, but there is a big gap between NAND and DRAM. This is where we go from latency of hundreds of microseconds down to tens of nanoseconds. So that is the gap that we'd like to fill. And certainly there are new memory technologies that help us fill that gap. So that's the other problem. NAND is too slow. So let's sum that up. So what are our limitations? DRAM costs too much. NAND, it's latency. The latency is too long, specifically the read latency for storage systems. Okay, so what do we want to do about that? Well, we have this general category called emerging memory. I don't even call it persistent memory or storage class memory. It's just all different types of memory that are coming forward. And from talking to customers, what we hear is that it has to be a cost about 1/3 the DRAM cost or price in order to be interesting. We used to say half, and now it seems to be 1/3. Seems to be the good target. How about latency? Well, the latency, the read latency of an emerging memory needs to be below 1 microsecond. And I mean for the system, not just the memory chip itself, not just that simple element, but it has to be all the way through. And as a matter of fact, there's only some workloads that can be handled at 1 microsecond. And those are some of the streaming workloads, can be 1 microsecond. But you have to get down to actually 500 nanoseconds in order for it to be used for all workloads. So that's what we're hearing from architects today. Well, in this category of emerging memory, does it even exist? Does something like this even exist? So I used this slide a couple of years ago at a talk I gave at Flash Memory Summit. And these don't even come close to all the switching mechanisms. There's actually an excellent talk and paper. I wish it was on video, but a guy goes through and presents this great memory switching, and it turns out it's a banana. He put 2 electrodes in a banana and showed it switch. So I like to say any fool can get anything to switch, just about. So there's lots and lots of switching mechanisms. Now, he had a talk yesterday, I believe, which was more on the physics itself and the mechanisms of switching. So I'm not going to go into that. But this chart gives you some idea of the diversity of physical effects that are there. And there's probably half a dozen missing from this chart. So the bottom line here is there's too many switching mechanisms. There's almost an abundance of choices. But let's dive in to a couple that have seen some work being done over the last decade. And on the far left is MRAM, specifically spin-torque MRAM. That's the latest type, which gives us the speed we need. The middle would be PCM. It's phase change memory. Years ago, I like to call 3D Crosspoint rebranded phase change. I see Amber in the back has shown up now, so I'll pick on Amber later. So Intel has a lot of names for this. This is Optane technology, 3D Crosspoint. The mechanism is known as phase change memory. And on the far right is resistive RAM. So these are the 3 that have been researched a lot. There has been some limited commercialization of these technologies, both in the case of standalone as well as embedded memory. So instead of getting into the physics, the science behind it, let's look at companies. Let's look at who's doing what in this area. And this tends to change every couple of years, so I had to update this chart. So on the far left, I spent the past couple of years working on spin-torque MRAM. And one of the places where there's a really good value proposition for spin-torque MRAM is in the embedded space. So as an embedded memory, we now have announced there are 4 different foundries, 3 of which you can design on their PDK right now with spin-torque MRAM at a 28 or 22 nanometer node. So this technology is really coming forward. And that's being used for code storage as well as some caching. Now, in the standalone space, there's one company, which is Everspin, which has brought products to market. And so we're going to talk about them a little bit later in that area. Now, how about in the middle? In the middle with phase change memory, there's Intel and Micron, who unfortunately are getting divorced after a number of years, but have pursued this technology. And we're going to talk quite a bit about 3D Crosspoint and its relevance to both storage and memory systems. In the embedded space, STMicroelectronics is the lone holdout, but continues to develop this technology for embedded. And then finally, in resistive RAM, I used to have a lot more companies up here. It seems like resistive RAM is slowing down a little bit. We're not seeing the same adoption in the industry, et cetera. So there's fewer companies pursuing it. In the embedded space, Panasonic has developed a very nice technology, and Crossbar also has licensed their technology to Foundry, although we haven't seen as much uptake of that technology as we once thought. In the standalone space, Adesto has shown their version of resistive RAM, which is conductive bridging RAM, and that's for relatively low density and almost can be considered embedded. And then at Flash Memory Summit this year, Sony talked about pursuing a resistive RAM technology that is in the hundreds of gigabit range, but is still years out. So let's focus in on things which are shipping, certainly sampling, and products that are shipping, because again, we want to apply this to our data center, to our reasoning system, and we want to see what can we build with these emerging memories that exist today. Now I realize, and even later today there'll be a talk on another technology. There are dreams of many other sorts of technologies. I put a splash of letters up here because it always seems like there's a new one every year that gets talked about. But we don't see evidence of that. There's no samples, there's no products, there's nothing we can build with that. So let's be mindful of these other devices. Although I'm still really curious about Micron's new memory B and when we're going to see that, what it is. Okay, so let's go back to the key question. Does such an emerging memory exist that gives us 1/3 the cost of DRAM and a read latency of less than 1 microsecond in the system? 3D XPoint doesn't really cost 1/3 of DRAM, according to my friend Mark Webb. And the latency is not less than 1 microsecond. Oh, that's a problem. How about MRAM? Okay, let's look at MRAM. Okay, MRAM's got the low latency, but if there was a hell no symbol for cost, I would have used that. I mean, it's not even close. It's really, really expensive. Yeah, middle finger. Okay, yeah, you're right. I didn't think of that. Good ad, good ad. I like that. Oh, so that's not good. That's not good. Okay, so our emerging memory candidates, neither of them meet our targets. And this is one of the lessons, guys, is that, you know, we keep setting up these targets. I actually don't like storage class memory as a definition. If you go back to the original IBM paper, they defined something which my 30 years experience tells me will never happen. So we have to be a little bit careful about that. And so I want to follow on that comment with, I call it the R word. I don't like to say it, replacements. And those of you old enough to remember The Graduate, that's what it's taken from. But there are no replacements. There are no one-to-one replacements in the memory business. And I could go back in history and prove that to you. The system always changes around the lowest cost memory, the smallest cell size. So stop looking for those replacement technologies. They don't exist. They're not going to exist. So we're moving from a NAND DRAM world to one with combinations of memory. So now let's apply that concept to the technologies I just showed, and also talk about what products are being built with those combinations of technologies. Okay, so on 3D XPoint, what can we do? Well, we can combine that on the memory bus itself with other DIMMs of DRAM, and to give us a winning combination to give us that reduced latency. So that allows us to achieve very low latency from a system point of view. So maybe the raw memory technology itself didn't give us that 500 nanosecond read latency we wanted, but how can we architect around DRAM and combine the two, 3D XPoint plus DRAM, to get there? Didn't do anything for cost, though. So again, I think that's one of the challenge for the manufacturers here, is keep bringing the cost of that technology down. How about an MRAM? Well, in MRAM, we had a cost problem, so let's combine it with NAND. NAND is a lot cheaper than DRAM. How do we combine it? And so by combining MRAM and NAND and working those two together in a system, we can achieve our goals, both low cost and low latency. Okay, so what are some products? Again, Flash Memory Summit was last month, so good time to talk about this. What are some products that we saw at Flash Memory Summit that featured emerging memory and actual things that were being demoed? Let's put it that way. Well, certainly Intel Optane DIMMs are very exciting. And this is putting that technology, 3D XPoint, putting it on the DDR bus. So Intel has done a variant of the DDR4 interface, and you put both of these types of modules there. And this came straight from their talk that they gave at Flash Memory Summit. And what we can see is, even in a module, these are very high capacity. Hundreds of gigabytes going to terabytes on a single DIMM. That's pretty exciting, especially when DRAM scaling is slowing down. And has been pointed out, even on DDR5, we're kind of expecting the highest capacity might be 32 gigabytes of DRAM on a DIMM. So these are really big numbers. So nice job there on the capacity. Now, Intel is focused very heavily on architecting the whole system to make it useful. And I think that's been an excellent effort that we as a memory community owe a debt to Intel in sponsoring that work. Part of that has been done through SNIA in the persistent memory twig. And it's a total effort to look at the architecture, the software, the hardware, everything necessary to take these new memory technologies and make them as useful as possible. So this chart here is showing latency, showing the stack up of the drive itself, the controller, and the software, and how by architecting all the way down to a special variant of the DDR4 bus, what that looks like. And what they're saying is we got the latency really close to 0. Unfortunately, it's not less than 1 microsecond, but it is just a couple microseconds. So, again, good job. And so what happens here is you have the DRAM as near memory, and then you use the Optane, the 3D crosspoint, as far memory, and that gets the overall system latency where you need to be. And then the bottom line is you can get terabytes of a memory pool that each of your processor clusters can talk to. Now, what's the only downside here? From my point of view, it's that it's Intel controlled. So if you want this technology, you're locked into Intel. If you want a wider supply base, kind of out of luck. So again, that's one of the disadvantages here. But we'll come back and talk about other efforts in that space. Now let's switch to our other technology, which was MRAM. And what did we see from IBM this year? We saw from IBM this flash core module that combines MRAM and NAND. And it uses just a small amount of MRAM for a very fast, persistent write cache. And that allows you to do logging, journaling inside. And the nice thing about this, as described by the architect, this is Brent Yardley from IBM that talked about it, is that it goes with the drive itself. So you no longer have to worry about backing up things that you might have outside of the drive. It's all internal. So this is a case where a small amount of MRAM with a large amount of NAND is giving us that low latency and that low cost that we want. So these are two of the technologies here that we talked about and where they fall on that latency spectrum. And they do a pretty good job of filling that in and giving us new options for storage and memory systems. There are a few other things, though, that are in there, and I'm not going to spend too much time in this talk discussing that. But let's talk about what are some of those other memory combinations or other things you might want to know about as we try and fill in this latency spectrum and give more options to storage system architects. So other stuff that I saw at Flash Memory Summit this year that you might find interesting. Apologize for the poor graphic. It looks like a spy graphic, etc. I think it largely was. Toshiba didn't post their presentation this year, but they announced something called XL NAND. And I like the graphic a lot because typically NAND is architected just to give you the highest density per square millimeter of bit cells. But what they're doing now is they're architecting inside the memory chip itself as all these small tiles. And when you have small tiles like that, you can do a massively parallel access, reduces the latency. So that was the nice part about it. And they're saying it's a 10-time reduced latency versus TLC. So again, this is not a new technology, but this is a new design architecture utilizing NAND to deliver lower latency. So that's also a trend. It's still not 1 microsecond. Sorry about that. But it does give us something that's new. How would you use this? And I think the way you would use it seems to be a market that it's starting to get going, which is very low latency SSDs attached to compute nodes that are not part of the storage system. Maybe they're attached to the networking system itself, somewhere like that. So there seems to be this development of new capabilities or new products that are trying to attack that market for low latency SSD. There are some competitors here. Intel has their Optane SSD, which is 3D crosspoint itself, which is out there in the market. And there's also Samsung ZNAND, which is doing something similar, which is let's just make NAND faster. So that's one of the things that I saw that also helps fill in that latency spectrum that we talked about. What's an activity that goes outside of that Intel-controlled environment is in JEDEC. There's work being done on something called NVDIMP. And I know there's multiple versions of NVDIM. We seem to like funky nomenclature in this industry. Too many letters and hard to keep track. You need a decoder ring. But the idea here is that this now, you re-architect the DDR5 bus to have a protocol which handles non-deterministic behavior. So non-volatile memory needs non-deterministic behavior. When you give a write command to an NVM, it doesn't know necessarily how long it's going to take to write. So it needs to have that ability to stall the host, etc. So this is an effort to do that without interrupting the progress of the DRAM on the same bus. So we're headed towards a future here where the memory bus is used for two different types of memory, volatile and non-volatile, with different characteristics. So we need a different protocol. And Bill Gervasi, who's going to be speaking later today about Nantero's technology, he talks about it being a non-determinist credit-based system. He says time for cleanup, but basically it's holding off the host and having this ability to do both. So this is a very interesting activity, and it is intended to be an open standard. It'll compete with the Intel Optane DIMMs, but it's backed by all the major memory companies. Now if we could just get a major processor company, AMD, I'm looking at you, to sign up, then things would be good. So I think that's what's needed here is still support from the processor companies. So this is something to keep track of. So let's sum up. This is kind of what I put together for you, your cheat sheet, your watch list, things I learned from Flash Memory Summit this year, things to keep watching. I think the Everspin MRAM in low latency SSDs is an interesting one. We'll see how IBM does with their Flash Core module, which is the first implementation of this. I think Intel's 3D XPoint in the Optane DIMMs for server memory continue to be a very interesting space. It's easy to make fun of Intel and say you overpromised and underdelivered, but at the same time, we do expect that hundreds of millions of dollars of 3D XPoint will be shipped within the next few years. So it is still the largest leading emerging memory effort that's out there. So, so I'll rein in my making too much fun of Intel. The Toshiba XL NAND, I think we're going to see more of this, how to make NAND faster and give us lower latency. And then finally that NVDIMM-P. So that's your watch list. Now let's go back and let's load Dr. Moda and talk about intuition at the edge. So I'm going to switch gears. So this is a really different topic. It's one I personally find extremely interesting. Now, what are some things that Dr. Moda has taught us? And this came out of a project IBM called True North. I think they have a new name for it now. I don't happen to know what that is. Your intuition system in your brain operates on 18 watts of power. You do a lot on 18 watts. Give yourself an A+. All right, way to go, brain. You are super efficient. If we took a von Neumann architecture, took it to the edge to do everything your intuition system does, that takes more than 20 gigawatts. In other words, it ain't working. You cannot use a von Neumann architecture. It will not be energy efficient enough to do your intuition job at the edge. Also, if we look at the architecture of the monkey brain, what we see is a lot of little compute nodes with a lot of networking. And it's quite fascinating, actually, to follow through that, the different elements of your brain and how it's networked. So we have a highly, highly networked, again, it's what IBM, I think, used to call in the past mesh computing. And so it's an old idea brought back again. How can we implement that? Now, one of the things that there's very good evidence for, including excellent academic papers and some industry papers now, are showing that trained neural nets perform that lightning-fast intuition. Now that makes a lot of sense, because when I showed you the picture of the woman at the very top, you called up immediately a model from your associative memory. In other words, you store all these models. You know, if I said the word room to you, you'd immediately call up a model. What does it look like, et cetera. So you have all these models. Makes sense that we would have these trained models stored somewhere in our brain. And neural nets do that extremely well. Now, an interesting way that you can use emerging memory is to hold the weight inside a trained neural net. So again, that's the way we're storing information, and it's a very compact way of storing. And when I say hold a weight or an analog memory, this is like MLC plus. This is lots and lots of levels. And I'll show you a little bit how we utilize this. Once we have the weights, then we want to access this array in parallel and then sum the weights to choose which model is the best to apply to the situation. So that's using what I call analog combined circuitry to run that through and then find that correct model. And keep in mind this is an approximate, right? Our intuition system gives us an approximate answer. It doesn't need to be precise. So the most efficient implementation is using analog memory, and that might be 6 or more levels per cell. I mean, again, IBM did some work on this that showed 5 to 6 levels is particularly good for this. Here's a nice thing. You don't need 7 or 5 nanometer processing. And one of the most amazing things that I've seen is we see 28 nanometer chips utilizing this technology outperforming 14 or 16 nanometer FinFET by a lot. Now that's power efficiency, that's prediction accuracy, it's the architecture. The architecture is much better than using a GPU and doing lots of matrix math. So as the architecture changes, the cost paradigm changes. Now this makes sense to do at the edge. And some of those places we'll talk about in a minute are in vision or image processing. How many of you have heard of this company called Mythic IC? Okay, very few. And maybe a few years from now you'll think back and say, yeah, I heard about that. They're a startup. I don't know if they'll succeed. But they're doing something very interesting, and I also like that they have competitors. There's one called Sentient in Southern California. They did a paper at Hot Chips that was a fascinating paper. Some of their members don't like it, but their CTO went and posted all the slides online and did a full explanation. So if you're interested in this topic, search Mythic at Hot Chips 2018, and you can find a very, very good description of their technology and how they implement it, as well as a good walkthrough of neural nets and why you should care. I'm going to touch on a couple things really quickly. Over on the right-hand side, this is the memory array itself, just shown as a 3x3. So each individual memory cell that's acting as an analog device, think of it as a variable resistor. And then what we're doing down here is we're actually accessing, we're figuring out how much current when we access all these things in parallel. So that is what helps us decide what model to choose. Now it's a blended system because while this is the neural net in the middle in this single tile, you can see that there's some digital logic using von Neumann concepts that are driving it. So it's not just a non-von Neumann machine, it's a mixture, a blend of the two. Then one of the things we mentioned very quickly when we talked about the brain is that there's several compute nodes and then you put them together in this mesh or sea of tiles. So again, this architecture is very close to how our brain operates and gives us results similar to how our brain operates. And they plan on using it for vision and image recognition and voice recognition right now. They're currently using embedded NOR flash because it exists. It's easy to integrate, and it holds those weights in that analog mode. Okay, another company, oh, well, that's my takeaway for it, what you get out of that. Another company that presented at Flash Memory Summit was Crossbar, and what's interesting is Crossbar has kind of gone in this direction of AI and the application for resistive RAM in that space. And they also talked about, here's their specific describing the flow of how information goes through and how an RRAM array in a trained neural net can do that. So that's, I think, an interesting question, is RRAM a technology which is especially suited for analog memory and neural nets? Okay, so those are two examples of companies that are doing interesting things in this space. So one of my favorite questions to ask, whether it's somebody else speaking or when I'm preparing to speak, is why do I care? And hopefully not too many of you are thinking that right now. Hopefully I've made my case of why you care. But let's recap a little bit. What is emerging memory enabling in artificial intelligence? And I think in the data center it comes down to this. How do I get terabytes of memory, a larger memory pool that I can access? More data, better decisions, better training, better decisions, more precise outcomes. So how do we get that larger amount of memory to operate on? On the edge, we talked about having this analog memory in this new architecture and then giving us this brand new capability, which our brain does, but our compute systems don't do very well, which is that lightning fast intuition at very low power. So again, I think this is the major takeaway of how I am stating that emerging memory accelerates us for AI. Okay, final wrap-up, takeaway points. Your brain has two distinct systems. And I saw more hands go up, so let's see it again. How many now believe this? Yeah, I think there's a lot more hands. Okay. And so good. I think I've made that point there. Our reasoning systems that are based on DRAM and NAND need reduced latency and cost. And I gave you very specific numbers about what we want to achieve. Unfortunately, none of our memory candidates do a one-to-one replacement. And so stop thinking about memory as a one-to-one replacement, but think about combinations. How do we combine different memory technologies to achieve the system-level goal? And then in the last section, I wrapped up with the intuition systems really do require that new architecture to get us to operate at low power. And we utilize emerging memory as analog, in an analog mode to hold those weights. And the goal here is to accelerate both the performance and the adoption of AI systems. Okay, advertisements. I get to wrap up finally with advertisements. So Persistent Memory Summit is coming. This is a very popular event. If you haven't signed up before, you can literally register right now. You can take out your laptop and bring it up and register right now. And I advise you to do it because it's standing room only. And I think the progression of the industry can be clearly seen through every year the advance in persistent memory adoption at that. And then finally, this is my advertisement. And if you want to follow me, you can track me on LinkedIn or on Twitter. Okay. Very good. Thank you very much. Do I get to introduce Amber? That could be dangerous.
We have time for questions because we have 10 minutes.
Good. Thank you.
I don't know where that is. Lucy has it.
Lucy. All right, raise your hand if you got a question.
Dave, you might want to mention why a persistent memory summit is being held here instead of downtown San Jose this year.
I don't know the answer to that, Jim. Jim, would you please give us the answer of why it's being held here? It's huge. It's huge.
Jim Pappas finally gave in. Other questions? If not, all right, thanks, Dave.
Oh, Tom's
Oh,
raising his
Tom.
hand.
I'll give you one.
He doesn't need a mic.
Probably not. Can you hear me? So Dave, one thing you didn't mention on some of the neural network processing is you sort of indirectly got into it with the in-memory processing, and in particular, I know because of your background, maybe you use Spintronics. Speak a little bit about those two items.
Yeah, I think
Maybe
there's.
you wanna repeat those.
I think there's two different spaces, and so yeah, I'll repeat the question, or I'll rephrase the question from Tom. He was talking about to widen out a little bit and talk about the application of emerging memory to more of the tasks. I focused on the intuition system at the edge. There certainly is, and I think NVIDIA does a very good job of explaining it. So if you want to reference material of why we do training in the data center, we do training right now today with GPUs and lots of SRAM, and sometimes we use DRAM. So that's the training function done in the data center. Edge we talked about. In the data center for training, SRAM scaling also has had difficulty and is getting more and more expensive. So there is a need to bring more memory into that space, and in particular, to have it be persistent. This is, in particular, is a task where that standalone STMRAM can go and offer new capabilities in that training function. That can be very helpful in as you're doing the MAC operations and doing that matrix operation, to have that be non-volatile and be able to store entries at relatively low power and go back and forth. So I think that would be my quick way of answering that. That there's application for other emerging memories to other parts of the AI system in the data center for training.
I'm trying to think ahead of this. Are there any implications as you do this design for less network traffic, say over cellular networks, because you're able to do more processing?
Sure. Yeah.
This is my daughter, by the way. Thanks, Lizzie. So that because you're able to do more processing at the edge, you're not shipping back and forth all the data to the server farms, and perhaps more latency in my great phone here, and less latency in the phone, and less data getting stored where it can be mined by people that I don't want it to be mined by.
No question. There are not two levels in an IoT to data center system. I've seen talks by Oracle before that there's 5 different levels. You store and process information of different complexity at each level. In other words, if I want to do something locally and make a decision, I don't want to go back to a data center, AWS data center, hundreds to thousands of miles away. I want to do it right there. There is a time and cost penalty every time you transmit data a long distance. Sometimes referred to as fog computing. Intelligence at the edge. How do we do more decision making locally and store less and less, or store more complex information all the way back at the data center? So I think that drives the embedded adoption of MRAM in particular, giving us a high density option of an emerging memory, and allows that integration directly into the SoC. You can see it in your own phone, though, too, is that the amount of storage capability you have in your own phone is kind of plateaued over the last couple of years. Now we're talking about how do we enable sensors to have enough memory, enough intelligence to do the job so that we can even unburden the mobile processor. So I think it's that multiple layers that we have to think about.
So Dave, we've been watching persistent memory emerge for a long time. In your crystal ball, what do you see in 5 years for?
Sure. What's
will
taking
we call
so
it something
long?
other than emerging?
When the hell are you going to get there? Yes, this is a common question. Usually I'm the moderator and I get to shout that at the panelists. What's taking so long? It's a very good question. I think, again, the leading effort is the total effort that Intel has done. I would continue to look for when do Intel processors ship with the right memory controller integrated that allow access to persistent memory. That's still somewhat limited. Myself, I'm looking at 2021 and beyond, which is a little more conservative than some other estimates. But I think it is taking a while. The NVDIMM portion is still very niche-y. It's still quite small. I hear those producers complaining that they're not shipping enough of it. So again, I think it's going to take still years of time. I don't think this is a hockey stick in 2019. Okay.
All right,
I
thanks,
think
Dave.
we've run out of questions.
All right, our next speaker is Amber Huffman, fellow from Intel. She's Director of Storage Interfaces in the Non-Volatile Memory Solutions Group at Intel. Her leadership role in industry standards efforts includes forming and chairing the NVM Express work group, a consortium of companies working to define a standardized interface for PCI Express-based solid-state drives. Amber chairs the board of directors for the NVMe work group and the Open NAND Flash Interface work group. She was a lead author and editor on the NVMe specification, ONFI specification, and the Advanced Host Controller Interface specification. Amber has been awarded over 20 patents in storage architecture, and she's a superwoman of Flash.
Thank you so much, Mark, and
Yeah.
thank you, Dave, for throwing a few things my way here and there. So what I wanted to talk to you today about was the solid-state transformation of the data center. I was asked to maybe do a walkthrough a little bit of time, so I had fun going back in my archives and seeing what we've done together as an industry. So just disclaimers, so make sure there's going to be a test, so make sure you read all that. So one thing I wanted to start out with is zettabytes. I didn't really even know what zettabytes were until I actually started working the past few years of hearing petabytes to zettabytes. And what you can see is that the edge and data centers and endpoints are driving just a tsunami of data. And so there's no better time for being in storage than what we see now. And so it's only coming, Dave talked eloquently about how in AI, you are absolutely needing more and more data, and that the thirst for data is increasing. So there's a lot here, and what we need is faster and faster solid state drives and persistent memory to take advantage of that. So in today's talk, what I wanted to do is talk about the industry transformation to embrace NVM and how we can continue to do that together. So I've almost got a past look at the past 10 years of what have we done together and how have we shifted as we move forward to really realize what we have in the NVM industry. So if we look at the journey beginning, going back to 2000, we really had, when I started at Intel, I was working on software ATA, which was even a precursor to serial ATA. How could I make hard drives faster and offload them into system memory with faster algorithms? It was fascinating, but we didn't have these tiers in the middle. So how did we get to where we are? If you go back a decade at IDF in 2007, I was talking about, hey, PC could be a driver of NAND growth, and SSD to become the new killer application of NAND flash. So it's hard to remember for those of us in this room when NAND was a potential killer application. For SSDs would be a killer application for NAND. So where have we come? So what we've done over the past decade is gone from, could NAND SSDs be part of this tiering, this memory hierarchy? And how did we get here? So the first thing I wanted to talk about was the need for the Open NAND Flash interface. So if we scroll back, we had no standard NAND interface going back to the time in 2005, 2004. So at least my experience when I was starting on SSDs at Intel, one of our issues was, how do I even design an SSD interface? We had Toshiba, we had Samsung, we had many smaller NAND vendors, and what we were struggling with is, how do I even implement solidly an ASIC for an SSD? What could I do? And so the challenge was, basically the way the industry worked at that time was Samsung would publish their latest data sheet, and everybody else would then adjust for whatever the new developments were. And so we really, to make the ambitions grow of what we wanted to do in the SSD industry, we had to address that. So then enter ONFI. And so what we did is, if you go back, and sorry for the odd formatting, one of the fonts did not translate. If you go back to ONFI, what happened is back in 2006, what we did is we first delivered we codified commonalities and then started to scale for SSDs. And then we started increasing the performance for SSDs. I don't know if we can remember what we've all done together over the past decade is, if you scroll back, NAND originally in 2005 was 40 megabytes per second was the interface to the NAND chip. And so we have gone to where we've scaled from, in ONFI 1.0, we went to 133 megabytes per second, then we went to 266, 400, and brought over the DRAM learnings, and we scaled in less than 2 years. And then we scaled for the SSD industry. So obviously one thing that many of you in this room know is ONFI was a coalition of the small companies of the Micron and the SK Hynix and the Intel. And so what we did is we worked with JEDEC and formed an ONFI-JEDEC collaboration. And then what we were able to do through that is work with Samsung and Toshiba to really bring together and unify the industry on how we had commonality in the most important parts of the NAND interface, such that all of us could build SSD controllers confidently and move forward with the scale of our industry ambitions. Then we had steady innovation year over year over year. We added some features. We went to 800 megabytes per second. Then I'll talk in a second about 1200, but just continuing over and over time to deliver steady innovation and keep pace with SSD needs. So up to today, we had, in 2014, we delivered 800 megatransfers per second. 2017 delivered 1,200 megatransfers per second. And so we've continued to keep pace with where NAND needs to go in order to hit SSD needs and develop that NAND tier. And so what are we seeing then? Should we just keep going? I mean, I started out at 40 megabytes per second, and now we're 1,200, so we should just go 2,400. So one thing I wanted to say is NAND is an amazing technology, but we've really reached at the scaling of the individual NAND device, we've reached where I believe we should go. I mean, maybe we go slightly higher, but what these charts are saying is that as you keep increasing your data rate, you're getting diminishing returns at the NAND. So I'm not going to be back here in 2 years telling you we've scaled to 1,600 megatransfers per second or 2,000 at the NAND. What this is saying is we've reached the end of our ambitions with NAND in terms of at an individual NAND layer unless we get a breakthrough in the NAND media. You just really have, I just get scaling where I'm just paying power and I'm not getting a system level benefit or an SSD level benefit to bring forward. So that was our first pass is if we're going to deliver a NAND SSD tier, first off, we have to be able to have NAND attach in a big way, as many of us have 40 NAND sites, 80 NAND sites, 120 NAND sites in our device. And how do we go forward and be confident about I can use Samsung, I can use Toshiba, I can use Intel, I can use Micron. So as an industry together, we've delivered that. And what I wanted to get across in this talk is one of the most important things is those of us in this room, us working together and figuring out what we want to do. When we first started talking about, in 2004, about starting ONFI, we kind of got laughed at quite a bit. Because it's like, Intel, you don't even own NAND. What are you talking about? Because this is pre-Intel Micron NAND merger. So I just wanted to, us in this room, that's how we move things forward. So now I wanted to talk about the path to NVM Express and what we need to continue to do. So ONFI work is pretty much done, and there's not continued, but NVM Express, we have way more. Are you guys asleep yet? You seem very sleepy. So I'm going to disclose something shocking. I'm terrible at names. NVM HCI, that was the original name of NVM Express. So this is back at Flash Memory Summit in 2009. I was out there talking about, hey, look at all this awesomeness of NVM HCI, an optimized interface for NVM. And what you can see here is we were really looking at it from a, hey, I've got an HCI controller, an NVM HCI, and I'm going to do this awesome caching and client, and I'm going to have this really cool thing where I just have NAND on a DIMM, and I just attach the NAND, and it's going to be awesome. And it was meant to be this very low-cost client capability. Well, sometimes our ambitions are failures, right? And so total misfire, right? We totally, that did not go anywhere. So I think that one of the things that I love books, as Dave does, and one of the things that I find fascinating is failure. You know, the growth mindset books by Carol Dweck of Stanford are fascinating. Of how do we really evolve things? It's by failing and then picking yourself up and moving to the next thing. So NVM HCI, big failure. But it was a springboard for enterprise. So what we did is we figured out that, hey, as an industry, we figured out that look at all these PCIe SSDs that are happening, all these Fusion IO SSDs. How do we, in the same way with ONFI, we thought about how do I enable NAND for a broad-based ambition of adoption in the industry through standards? I need to do the same thing. We as the industry need to do the same thing for PCIe SSDs in the enterprise. And so you saw Fusion and you saw a lot of different companies doing things, but not in a way that will scale for the industry. And so why not put a word like enterprise in front of NVM HCI? That sounds really good. So that's what we did. So how do we address the gap? We talked about enterprise NVM HCI and how do we deliver enterprise NVM HCI and the goals and timeline. And of course, the first thing I did was I said, you know, we should just extend what NVM HCI from client was originally intended to be, just an extension of AHCI. And so I was like, for enterprise, OK, I have to tweak a few things, but that's fine. Well, that's where all of us come together and solve problems together. And I remember Don Walker from Dell. He just like shook me and said, no, you are not going to just extend this client thing to enterprise. We need to clean this up. And what he said is, you know, hey, we're going to NVM Express, or Enterprise NVM HCI of the time, is going to revolutionize the industry. We cannot build off of some, you know, glass, you know, house of cards. We have to have the really solid foundation and do the absolute best we can. And so Don pushed me and said, no, we have to go start from scratch. And that's how Don, Peter, several of us got together and said, OK, what do we do for principles of enterprise NVM HCI? We started out with, you know, back in 2010, we talked about, OK, the first bucket was get rid of performance bottlenecks we see in other interfaces. So for example, if you look at AHCI, you have register MMIO reads that cost you, you know, a microsecond each. You've got to get rid of all of those. You have to simplify the decoding. So one of the challenges that we saw with really large-scale SSD ambitions is I need to be able to hardware automate everything. And if you look at SAS or serial ATA, it becomes pretty challenging to hardware automate certain things because of boutique things. So how do we get to one read and one write? Another big bucket was a streamlined command set, again, to realize that ambition of how do I hardware automate. Then into enterprise features. How do I have encryption? How do I have the end-to-end data protection? How do I have solid error reporting? And then lastly, how do I get a scalable architecture? So something I'll come back to more and more at the end is what you'll experience is, you know, we look back, and this is 2010, but we really started working on this like 2007. And what I'll give away a big secret, NVMe didn't ship till 2014. When you have, and it really didn't gain steam until 2016. And so one of the things as an industry that we have to be super clear on is where are we going? It takes a long time to get anywhere. As you guys, as in SNIA, as we've been working through the persistent memory twig and all of these things, it takes a long time to gain that momentum and truly deliver a massive innovation. So as an industry, we really have to know where we're going. And so that's why I think it's super, super important that we focus on what are we trying to build. And so from the very beginning, with NAND, we knew that NAND, I mean, I remember NAND was going to die, you know, from ever since I've been working on it. But it's not dead yet, right? But we always knew there was something else coming. And so we needed to define NVM Express from the ground up to make sure that we could accomplish the ambition of things like 3D Crosspoint. So NVM Express was born in 2011, in March of 2011. And so we had the, you know, this board of directors that included, you know, a few companies that no longer exist, but Micron, EMC, many of us in this room. And it really delivered efficient SSD performance. And so if we look all the way back, you know, we got rid of the uncacheable register reads. We got the MSIX and interrupt steering so we could get up to 1 million IOPS. We really maximized queue depth and efficiency for 4K commands. And then we really focused on how do we develop the ecosystem. We looked at the interop program from the very start. How do we broadly scale and make sure that we address things together? And major drivers for all OSs. I think something that was a critical breakthrough in NVMe was we had drivers available before the first SSDs. That's really one of the things that made NVMe go versus potential competitors of the time. Say, many of you in this room might have remembered the quote-unquote war with SCSI Express, right? A lot of it was just putting your head to the wind and really delivering and building out the ecosystem where everyone could thrive. We then focused on how do we build out the enterprise feature set. How did we add multipath support and reservations and other capabilities and just continue to build? And so another key thing that I see that SNIA does so well is pick a point to go and just keep going and build out the capabilities over time. And we get there as an industry together. And then finally we shipped. I don't know if I'm going to get in trouble if Intel sees that I've included a Samsung picture in the first, but Intel shipped very shortly thereafter. So we had the first PlugFest in May of 2013 with 11 companies. We had the first product announcement from Samsung in July of 2013, and then they shipped they really shipped later in the year, as did Intel. And so we had 2 drives out in the market in 2013. And it really delivered in performance. So this talks about, hey, let's look at the performance. We had awesome random reads, awesome random writes, very good sequential performance, really taking advantage of PCI Express. And so how do we build on a foundation that scales is another key thing that I think through. So if we look at today, PCI Gen 4 is starting to be coming out into the marketplace over the next year. And you have even people working on PCI Gen 5. PCI Gen 5, the specification is on track to finish in the next year or so. I shouldn't announce anything on PCI SIG. Many of you are SIG members and know much more than I do. But we're just scaling, and that sequential performance we can continue to deliver with NAND or other media. And then how do we do it efficiently and with low latency? There was a lot of debate early on in NVM Express about, why are we worrying about all this efficiency? Why does that matter? And it doesn't matter for NAND. I mean, when I look at AHCI and how bad AHCI is, which I also was the author of for serial ATA programming interface versus NVMe, people would say, why are you focused so much on the efficient and latency of NVM Express? And it wasn't for NAND. It was for making sure that we didn't have to redo NVMe for new memories like 3D Crosspoint in the future. So it was super important for how do we get the average latency down. So this is just showing how all the way back, if we look at the average latency, just NVMe running on a PCI Gen 3 on the CPU is so much more lower latency than SAS or SATA. And that's really the focus we had to have. And with better quality of service. So getting to this curve here is, what does it look like for my interface latency for 4K random reads? I just fall off a cliff with my quality of service as well as with SAS, whereas I get consistent performance with NVMe. And shockingly, the analysts notice over time. And so people started to project that PCIe, mostly NVMe, would replace SATA and SAS over time. And one of the things that was exciting to me over the in the last quarter is that Intel, for the first time, shipped more terabytes in capacity on NVM Express than on serial ATA. So we truly are hitting a crossover in the industry. And we continue to add capabilities. So if we take a look at NVMe, we're just adding capabilities over time. One of the things we did is in 2014, we added NVMe 1.2. We added both client and server features. So for example, host memory buffer was a client feature of allowing you to utilize a host DRAM with the SSD. And whereas controller memory buffer, we try to, again, my whole theme is confusing people with naming. So host memory buffer, good thing for client. Controller memory buffer, more of a good thing for enterprise. So it's all about how you suck people into your work groups because they can't tell otherwise what you're talking about. No. And then we headed to new frontiers. So we went on to the management interface, then on to fabrics, and then driving innovation in the cloud. So something that we could really see we were hitting on something is, how do you find, just like with AI today, how did we get embraced by some of the up and coming, that we're not entrenched in any traditional focus area? So if we took a look at, we had the lightning design that Facebook did, and then just talking through why did they embrace NVMe. You had Google Cloud Platform all the way back in 2016 differentiating SCSI versus NVMe. And it all comes down to what we're showing here is this is the HDD latency of SAS and SATA. Then you go over to a NAND on SAS or SATA, and you get a really nice, milliseconds to microseconds. Then you go to NVMe, you get another bump. But you still have all of this latency in the media with NAND. And that's, the dream is to Optane. And I'll talk more about that dream. And then even more capabilities in NVMe revision 1.3. And so in revision 1.3, we added virtualization, we added directives, and just continuing, about a 2-year cadence on the specification for what people need and how we keep delivering for the industry. So we delivered streams, we delivered virtualization, and more. And so one of the key things with streams, starts to hit on a key point I want to talk to you about what's our North Star as we move forward in NVMe. Streams is hitting towards the what do we do to deal with some of the conflicting of where I have multiple tenants using a single drive. When I have so many tenants using one drive, I get these inherent conflicts. What am I going to do to really address that and make sure that I can have this very big drive be used by so many tenants and feel like a small drive? That's, I think, the biggest challenge of what we have moving forward. So here's the latest NVMe roadmap. I think where you're sitting, you should, put on your binoculars and make sure that you study this deeply. What we're doing is we have NVMe MI 1.1, so we have the management interface. We're adding enclosure management capabilities. So enclosure management features, making sure that you can have your LEDs and have everything else. We have NVMe over Fabrics 1.1. The key thing in NVMe over Fabrics 1.1 is two things. One is a new TCP transport layer that I'll talk a little bit more about. And the other is enhanced discovery. So one of the things that we are trying to do is make sure that when we originally delivered NVMe over Fabrics, we didn't really, our ambitions were not completely massive scale to start. We wanted to, take things in chunks. And so now, as we've gotten much more broad adoption, what we need to do is make sure that when you're out trying to figure out what's on the network, we have enhanced discovery capabilities so you can more easily find what's changed in the network. So you actually can be able to query, hey, what got added on, what moved, all of those things. And then NVMe 1.4. So both of the NVMe over Fabrics 1.1 and NVMe Management Interface 1.1 we're expecting to release by end of this year. NVMe itself, the core specification, the revision 1.4, we're anticipating to deliver that mid-next year. What that's got as anchor features is we have multipathing capability. One of the key things is just building out further and further a lot of our multipathing. So asymmetric namespace access is one of the key things. If Fred Knight is here, Fred can tell you to a great extent of the wonderful capabilities in ANA. What that's trying to do is make sure that if you have two paths to an SSD, how can you make sure that the path you're on, that you're on the optimal path currently, and then fail over to the one that's less optimal? Then we have persistent memory region. One of the capabilities that we're doing in that is essentially you take the controller memory buffer that has such an awesome name, and you think about, okay, that is for when it's volatile, is the controller memory buffer. What persistent memory region is giving you is a persistent controller memory buffer, essentially, but we just renamed it. So persistent memory region, what it's really giving you is this capability to have a way that you can have memory access to your SSD. So you may have, you can imagine some people thinking about in database applications, they may have a portion of the device that they want to use in a memory-like fashion for certain updates, for small updates, and then they want to use the vast majority of the SSD as NAND in a normal fashion. So that's what persistent memory region gives you. And then lastly, I/O determinism. Let me lead into I/O determinism is on the forefront of what I think we need to focus on next. So let me dive into that. So today's challenge that I really see is quality of service at scale. And I/O determinism is one mechanism going after that. But I wanted to talk with us about how we align on the real problem we need to go after next and how we do that together. So I am shamelessly stealing lots of pictures from a presentation that Chris Peterson and I gave together at Flash Memory Summit in 2017. So Facebook at scale, these are numbers from 2017, and so it's only gotten way, way bigger, right? So you talk about, 2 billion people join Facebook each month. It's just, that doesn't make sense. 2 billion something. It's something to something, but they're big numbers, right? They're really big numbers. That's my point. At scale, it's big. I sound like an engineer, right? So one of the things that's occurring is disaggregation, right? Disaggregation of storage that's happening over time. And you have a server where you really want to disaggregate because your CPU and your flash, in year one, you've balanced them. In year two, well, hey, on this particular server, maybe I need more flash, and so your needs have outstripped. But on the converse side, you may have, okay, I've got wasted CPU resource. So a critical thing that the disaggregation of flash or storage pooling that some people like to talk about is how do I not scale and tie two things together that don't need to be tied together? How do I not tie my CPU scaling to my flash scaling? And we're seeing that in all sorts of things. For example, I was in a conversation, earlier this week about how do I not tie my AI scaling to my core scaling, right? How do I make sure that I can independently scale these variables to deliver the best performance and the most optimized? And one thing you'll hear Chris talk about is dark flash and the evil of dark flash, right? Flash is not the cheapest thing ever. Some of our major cloud service providers are actually spending, I was very disappointed to learn, as an example, one of our cloud service providers that's one of the top Super 7 that they call them, they spend more money on, their most money spend is on memory, on DRAM. And the second most is on SSDs, and the third is on CPUs. And being from Intel, that was super sad. So a key thing is how do we disaggregate flash so that way you can avoid buying more flash than you need and really right-size your variables of CPU and memory and flash. So the challenge that Chris is seeing is that the NAND flash trend, if you look at it, is kind of crazy, right? So the NAND flash trend is we just keep growing our NAND flash capacity, which is awesome for everybody in this room. But what that leads to is a really big challenge. If you roll back a few years, people were attaching, say, I attach a terabyte M.2 SSD. That's awesome. Now I've got a 4 terabyte M.2 SSD. However, my application doesn't need 4 terabytes now. How do I now land more applications on a single SSD? And what does that mean to me as a shared resource? So what that means is I cry. So what you have here is, you've got your noisy neighbor problem. And so I have application B and C that are being very well behaved and just doing read requests. And then application A is just doing all these writes and just thrashing my SSD. So how do I live in that environment moving forward? And so what Chris was trying to give as a great example, I liked he couldn't get the rights to an image that I liked even more, which was a Ferrari in a herd of sheep, So how do you deal with that? I got this Ferrari, it's awesome, but what am I going to do with it? So we need to create that individual lanes, that individual racetrack for our awesome devices for us to really realize our ambitions moving forward. So if you look at this, this is a more realistic graph or real data showing what the problem is. What Chris is showing here is that if you have the percentile of this is my read latency, and this is a histogram or my requests. So most of my requests come in at between 90 and 100 microseconds of latency. That's what this is showing. But I have this, and I don't have much of a tail. Pretty much everything's cut off at 100 microseconds. So that's awesome. My problem here is that I have my tail, and my tail doesn't go that far. It only goes to like 130 microseconds. If you notice, what happens is I introduce 10% of 4K writes and 90% 4K reads. And that's my noisy neighbor from the last slide. All of a sudden, my worst case outlier went from 130 microseconds to 4 milliseconds. That's super sad, which is why he's crying. So that 35x, that is our industry challenge. What do we do to address this? So one thing that I've worked on the past few years is something called I/O determinism or NVM sets, and that's pretty cool. But what you guys heard about from Matthias yesterday was zone namespaces, and that's pretty cool. We need to get aligned on what the really cool thing is that we're all going to pull together on and deliver to really solve that problem of quality of service at scale that we're just running into now. There's all sorts of ways to go after it, but I see us almost in the same space of when I call back to, before when we were still enterprise NVMe HCI and noticing you had Fusion doing this and you had a different company doing that. we have to get together on what the true way is to solve quality of service at scale, because this problem is only becoming worse. And that's where I'd encourage you to get involved at NVMe and take a look at what we're doing in zone namespaces and other approaches. But we have to get on the same page of where we're going so that all of us can benefit, because it's a universal problem for our industry moving forward. So then I wanted to touch on briefly scaling the number of SSDs and how fabrics came to be. So if we talk about fabrics, why did we do NVMe over fabrics? I think it was because we were bored. I'm not sure. So this is the problem that EMC that laid out. So Mike Shapiro of DSSD, and then that got acquired by EMC for a very large amount of money. He was showing that if you look at, on the blue, it's the scale of the number of devices that people want to attach. I mean, in 2015, he was calling out, tens of SSDs. I remember trying to make the case to my management that you would really want to have 4 SSDs in the server, and they thought I was crazy back in the day. And then to hundreds of SSDs, and then to thousands of SSDs. But at the same time, you have on the right is the latency. So NVM Express with NAND, you're up here at 100 plus microseconds, and then you get to next-gen NVM, something like a 3D Crosspoint, and you end up very much down here if I want 20 microseconds. So the why is, how do you extend NVM Express to over fabrics? And so if we look at, I want to realize that this yellow is all my media time. When I get to next-gen NVM, I want to realize that benefit even if I'm across Ethernet, or I'm across OmniPath, or I'm across InfiniBand. I want to realize the benefit of the very fast SSDs and not lose it in translation. Because one thing that keeps happening is when you translate to something like iSCSI, you lose a ton. So any of the end-to-end features, so for example in SCSI, you have your command queue is 256 deep, but in NVMe I can have 32 queues of commands that are all very deep, or 200 queues of commands that are all very deep. And I have all the feature set. And I want to be able to use that end-to-end to get rid of translation that only adds latency. And so what we did is we created NVMe over fabrics. And what this is showing down here is, OK, I am creating a very thin host-side transport abstraction and a thin controller-side abstraction, but it's NVMe end-to-end. And so how do we realize that we only add 10 or 20 microseconds of latency? So this is back in 2015, and how do we focus on it? We wanted to leverage everything we did in NVMe. So we leveraged the namespaces, the controllers, the queuing, all of that we leveraged and kept the commonality. And so 90% common between them, so common commands, common as much as possible. And we delivered it in 2016. So we had, if you saw in June of 2016, we delivered NVMe over fabrics. We had a Linux host and target. We had more than 20 companies. And we had 10 companies showing less than 10 microseconds added latency and brought that to market. So, of course, you can tell my theme of we just have to keep adding over time. So the original NVMe over fabrics, we delivered RDMA as one, and that encompassed InfiniBand and encompassed Ethernet and whatnot. We also had Fiber Channel. What we've added is we've added TCP. So TCP is the new transport. It should be imminently ratified in NVMe. And so why add TCP? There's a couple reasons to add TCP. One is that our ambition to scale the discovery capabilities, part of that comes from TCP being added. That makes the discovery mechanism all much more simple in terms of management of the network. The second thing is that RDMA is great. Fiber Channel is great. There's a lot of stuff that's really great. How do I realize the benefit of NVMe if I have an existing infrastructure of a bunch of existing NICs that are TCP? If I don't have an RDMA NIC in my infrastructure and I have this huge infrastructure, say I'm a Facebook or a Azure or a Google, and I've got all these NICs, or if I'm I need to be able to go in and take advantage of NVMe without ripping out all of my network cards. And so that's what TCP is giving you. It may not be. There is absolutely zero debate that TCP is the most performance optimal solution versus what you could build. But it is the good enough. If I have an existing infrastructure and I want NVMe, I'm going to get 90% of the benefit or more. So if I take a look at using iSCSI, I'm talking about 100 microseconds of latency, even with of additional latency by doing that. If I go with TCP, I'm still in that 10 to 20 microsecond added ballpark, and I get the NVMe capabilities end to end. So it's a really exciting alternative to iSCSI to really realize the ambition of how do you get more NVMe SSDs in your network. And then I wanted to highlight software. I try to, forget about software as much as I can, but then the software people poke me, like Andy Rudolph's back there somewhere poking me. So software plays a critical role. So one of the things to take a look at here is this is a Alibaba Cloud storage infrastructure example. And what we're showing here is if they use SATA SSDs, they got IOPS per CPU core were only 200, and they were sad. And then when they went to NVMe and they still used the kernel, they scaled it 2x. But when they used SPDK, they ended up scaling by 10x, actually more like 15x. And so the benefit there of how do we get to optimize software such that when we're talking about the latency we're talking about, software matters. And so how do we deal with that and how do we optimize? So I can't finish without connectors and form factors. So it was funny going through my old archives of old presentations, what I found. So Jim will recognize this slide about U.2. So the predecessor, if we go back to 2011, and the SSD form factor work group that many of you were probably a part of, we talked about, hey, we need to create a 2.5-inch form factor for enterprise SSDs. And then it really started to take shape. We had the capability of you could plug in SAS, you could plug in SATA, you could plug in a by4 PCIe, you could do a by 2x2s to get dual ported, you could do all sorts of exciting stuff. So that was all the way back, 2013. We, as an industry, got together in 2010, 2011, realized it in 2013. And then I found us inventing M.2. I mean, I've almost tried to put this out of my memory, but if we look at this, this is a slide from 2011 of the Apple gum stick and M-SATA. And what do? These are not great things. And so what about an optimized caseless form factor, which turned into M.2? And so M.2 as an ambition of, hey, socket, if you guys remember, there's socket 1, socket 2, socket 3 of a storage only. There was a lot of frustration by many people about socket 3. About creating a by4 only storage capability. And we always thought that it was only for the future, that it was for this far off future. But people started using it right away. And so this all was from client. So what happened? We created U.2 and M.2, and we created it in the data center. We have been living with U.2 and M.2. We've lived with U.2 was, I must have a capability of having hard drives in my system. And M.2 is a client-derived solution that we've forced into data center. And what I wanted to highlight is, legacy keeps us in a legacy box, those legacy mindsets. So one of the things I wanted to highlight is one of the things that's emerging now is how do we start to take essentially the whiteboard that Don shook me back for NVMe and say, on form factors, we need to shake ourselves. We can't use the form factors derived from hard drives or client for the data center transformation we're doing now. And so what we've been doing over the past 2 years is putting together something called EDSFF. And so EDSFF is a scalable form factor for different usages. We have both a short and a long, and there's both a 1U and a 2U high. And what it does is it enables you to, another key thing in our data centers is we have precious number of PCIe lanes. We can't strand them all to being a storage-only connector of M.2 or U.2. We have to be able to use them for GPUs or for AI accelerators or for other things. And so that's what EDSFF is giving us, is the ability to put a connector down and then decide later, 2 years after I've designed my motherboard, what I use it for. So that's something I encourage you to get more involved in and take a look at, is EDSFF is really that next generation on form factors for where to go. And I never thought at the beginning of my career I'd ever talk mechanicals. So with all of that, I just wanted to highlight, we've delivered this NAND SSD tier. We have done that together over the past decade. It's been a lot of work. It's been connectors. It's been software. It's been fabrics. It's been fundamentally designing a NAND interface for the industry. But we've done that, and now we have the scale and a multi-billion-dollar business that many of us enjoy for NAND SSDs. But there's more. There's future NVM. So if I go back to IDF in 2011, we were talking about scalability for future NVM. We were dreaming of the future NVM coming to fruition. And so this was just an example of how do I get as low as I possibly can. There's a device called Chatham that we built at Intel to do. It was an FPGA that simulated the kind of latencies we thought that a 3D crosspoint could achieve, and just how do we hyper optimize from the start to hit 1 million IOPS with very low latency. So then we were looking at, this is from Flash Memory Summit and Hot Chips back all the way in 2013, and it was just saying, hey, there's all these different memories that Dave talked much more about than I could ever talk about. But if you look at it, what this is saying is, how do I fully exploit the next-gen non-volatile memory? What these dark blue and lightish blue, all of those are media latency, and they make you sad. And so then you get to the next generation memory and you're less sad, but then you got this red. What's that red? That red is the evilness of software. No, just kidding. So we had to work on the red, which is what NVMe was attempting to address, but we really had to even go even further. So then in 2016, you know, Intel and Micron both announced, hey, 3D crosspoint technology, it's awesome, we love it. And then into how do we reimagine the hierarchy? So if you look at, you know, we have DRAM, we have NAND SSDs. 3D crosspoint is a perfect technology to fit in between. So why do I care? This is an SSD picture. Why do I really care? Because I can reach a region of operation with 3D crosspoint and Intel Optane SSDs that I never could before. So what this shows is, this is an Intel P37 blah, blah, blah. You know, I'll get in trouble with the marketing people later. This is a NAND SSD along this curve, and it's showing the latency in microseconds at your 99th percentile. So what it's saying is, this is my tail latency, and if we look at what's our problem? Quality of service, right? Quality of service at scale is what matters to so many people, because they're going for service level agreements with their customers. And what this is saying is, I've got this tail with NAND, and NAND is just an evil thing because of its program and erases, right? It's a beautiful but evil thing. So what this is saying is, 3D crosspoint, I don't have the tail. There's no tail. I can be just perfectly vertical because I don't have all that erase and program that I can't give the quality of service that I need to give. So why does that matter? Let me show a proof point and talk about where are we going to the future. So this is an Intel, and sorry for the horrible font translation. So first off, if I take a P3700, so again, a NAND SSD, and I put an Optane in the box and don't do anything, I get 30% better performance on Cassandra database, which is an important database to many cloud customers. Then I go optimize with direct.io and Java optimizations, and I do that software thing that apparently software matters, and I get another 2.5x, right? So if I really focus on software, I can get so much more at a solution level. And then if I evolve and I go to persistent memory, I get a 9x, because essentially what persistent memory is about getting rid of me. Because with persistent memory, you don't need NVMe. It just goes away. It's load store. You don't need NVMe. We can just go away. Or I could go away. So, so cheer for me going away, and that we really get that 9x performance and really realize the ambition of persistent memory. And one of the things that I'm excited to say is Intel has actually sold for revenue our first qual sample of our persistent memory DIMMs. So despite it always taking a long time, and you know, if I think about NVMe from 2007 to 2014 for a ship, we have a long history of you know, persistent memory coming, but it is here. And so that emerging hierarchy is, we would, from an Intel perspective, we would say, we think Optane SSDs and Optane persistent memory are a great addition to this hierarchy so that you can optimize for that TCO. And with that, we have so many zettabytes, and we need to make sure in that hierarchy we are putting the zettabytes where you need it based on the workload and the TCO and the value you get to the customers. And with that, so we invented this future together. There's so many people in this room that I've worked with so closely over the past 10 years, and this has been us together with fits and starts of really stupid ideas by people like me of NVMe HCF for client, and then we fix each other, and we deliver something great together. And I really think over the next decade, we have more opportunity with scaling quality of service, with taking advantage of the new memory and the opportunity that provides. And I'm really excited to work with all of you on that. So that's my talk. Thanks. I think you guys get a break now, but if you want to, I can answer
we have time
questions.
for a question or two.
Excellent. Go ahead.
Lucy, can you wait for Lucy?
Oh, there's a mic. You must have a mic.
Great
We're
talk.
being
Andrew.
live streamed.
Do you have an update? I know that there's been yield issues with 3D XPoint, and the marriage is breaking up between Micron and Intel. Do you have any update on when? What you have said nothing about price. All you said was availability about 3D XPoint.
Have you ever learned about letting engineers know anything about price? They intentionally don't tell me the price. So I see the price at, just like you do. The only thing I would say about the quote-unquote marriage breaking up is that I think you just have to look at what is Intel's ambition. My ambition, so I actually joined the data center group at Intel 18 months ago, and I actually do real data center stuff now, which is frightening. We're about how do we optimize Optane for the data center. And so I think that fundamentally, I look at I think that there's more drama made of this than there needs to be. We are laser focused at delivering data center optimized performance. And I haven't seen that, this is my perspective, mine only, not Intel's. I've seen that's where we're going. And that's where we're going to deliver the most optimal Optane SSD and Optane persistent memory solution we can to deliver for the industry for the data center ambitions we have. And so we have so much AI, the amount of data AI needs, as Dave was talking about, it just is crazy. And so we really see we need to optimize for AI and where the data center's going.
All right, one last question.
Right here. Hi, Amber.
Hey.
NVMe was designed primarily as a block interface, but we see now the emergence of CMB and PMR, and you mentioned those as part of your talk. How do you see, again, the emerging of those new byte-level memories? Should be part of NVMe, or should be a new standard for accessing those types of memories?
I mean, my opinion is the amount of investment for the industry to truly optimize yet another thing in between NVMe and persistent memory, I think it's a big lift for a tweener, right? So that's where controller memory buffer and persistent memory region are a good opportunity for being able to get for something that's out over PCIe, being able to optimize your transfer to that. But fundamentally, I think you really end up with a persistent memory solution being what you do rather than trying to define yet another interface for that tweener. So, yeah. Thank you guys for your time. I appreciate it.
Yeah, thanks, Amber. Come back after the break for the Gen Z versus OpenCAPI. 10:40.
All right, I'm getting the high sign here. All right, hello and welcome to the final track of our main stage presentations for SDC. I'm Tom Talpe with Microsoft, and I'm also a SNIA Technical Council member. And I'm going to introduce our speakers, and I'll tell you briefly what we're going to do in this last leg. So for this track, we have two emerging interconnect efforts, OpenCAPI and Gen Z. And we have, the top of mind today in both system architecture as well as storage. They have implications on all of the above. So we have distinguished leads from each project, and they're each going to give a presentation. We're going to hold questions to the end of the second presentation. We're going to basically have a double header. We're going to do 30-ish, 35-ish minutes of OpenCAPI, and the same for Gen Z. And then we're going to have kind of a mini panel discussion. I'm going to field questions from the audience, and we'll have discussion among the people. A lot of people sort of expect a food fight. We're not going to have a food fight, and so I want to have a little bit of a discussion here so that everybody understands what's going on. All right. And so please hold your questions to the end of the second one, and there'll be plenty of time for that before lunch. C6 is not here. We're democratic, but they didn't put their name in the bin, I guess, for SDC. In any event, our first speaker will be Jeff Stukley from IBM. He's a senior technical staff member in the Systems and Technology Group, works in the area of system hardware architecture. His most recent work is on advanced memory architectures, that's interesting, cache coherence, and accelerator design. He's contributed to the development of numerous IBM products in the Power architecture family, most recently the Power 9 design. Jeff.
All right. Yeah, so food fight to be great. I noticed yesterday at lunch they had little feta cubes, which I think those are feta bites. And so we'd be throwing feta bites everywhere. Yeah, they decompress in your stomach. It's kind of, all right. Figured you guys think it's funny. Zettabytes, then fetabytes. All right, so I'm going to talk a bit about what we're doing with OpenCAPI, and some background, which a lot of it is in common with the Gen Z presentation, in common with previous presentations. So you'll kind of see how we're trying to at least address that. So industry-wise, we've got really two significant things that are quite dramatic compared to, like, say, my last 20 years in processor architecture. The last 20 years were spent making our CPUs go from 400 megahertz, I think was the first one I worked on, to somewhere in the 4 gigahertz range. And then, some number of years ago, probably 5 to 6, we capped out on that frequency, and we're having essentially Moore's law pains, right? No greater frequency parts. We are getting more transistors, but those transistors are at the same power that they were in previous designs. And so we end up having this huge problem trying to do everything with general purpose processors. So we've adopted accelerators. IBM just did this joint project with NVIDIA supercomputer. We now have the top 500 supercomputer in the world. And where do all the flops come from? They don't come from the general purpose processors. They come from the accelerators in NVIDIA. Those NVIDIA accelerators, though, need to talk to the network. They need to talk to host memory. And so that's kind of what the power processors become in those systems, is a way to tie accelerators together, tie emerging memory together, and tie networks together. But certainly we have to deal with accelerators and integrate accelerators. The other side of things is memory technologies, right? We now have a long list, as you guys have seen, of different emerging memory technologies. And we need to be able to figure out how to deploy those technologies in an efficient way, in a very dynamic way. And that's a big part of what we're trying to accomplish. So what does an accelerator want to be? And what we don't want it to be is a device that you talk to through a device driver that has high software overheads, that transfers a block of data to the accelerator churns on it for a while, and then sends the data back. That very much limits the ways in which you can deploy accelerators. We need the accelerators to be tightly coupled to the processor, to the host processor, and other accelerators in the system, and able to communicate through shared memory, right? So we want to be able to talk through accelerator to accelerator, accelerator to host through our shared memory model, just like multi-processor systems talk to each other. So if I got 8 CPUs in a box, you don't need device drivers to talk from one CPU to another. You want to be able to talk through shared memory. So that has implications on how we do addressing. We don't really like I/O MMUs. We like MMUs. We also want to be able to manage cache coherence. Once again, when I share data between 2 CPUs, I don't have to do a bunch of explicit cache flush instructions or things like that. That's sort of kind of 2 decades ago or whatever. We got lots of form factors. We have lots of different accelerators. Different applications require different accelerators, and so we want to have a very fluid, heterogeneous system. The other side of things is data centers want flexibility and openness. People don't want closed standards. They want to be able to go and buy processors from Intel, buy processors from AMD, buy processors from other vendors, IBM obviously, right? And they want to be able to mix accelerators across those ecosystems as well. So proprietary, bad, open, obviously a requirement going forward. So let's talk a little bit about that. So acceleration is becoming commonplace. The acceleration communication wants to be fast. PCIe, people have latencies in the 700 microsecond range, microseconds. That's a lot of time for a processor to be sitting there doing nothing, right? We're trying to execute in a CPU, trying to execute, I don't know, 4 instructions a cycle, 3 instructions a cycle. Those instructions are 250, they're a quarter of a nanosecond, right? So if I'm sitting there for 1,000 cycles waiting for an accelerator, that could have been 4,000 instructions that I wasted, right? Processors are expensive. We want to get full utilization of them. And if your processor thread's sitting there for 4,000 cycles waiting on memory or waiting on an accelerator, that really limits how well you can ship a little bit of work out to the accelerator and have it back. So we need to make things tightly coupled and low latency. So to get this to happen, though, once again, we need this full industry participation, right? It's got to be, in the past, IBM has done memory in this way, but in proprietary standards. We've done accelerators also in proprietary standards. But we want to be able to have a broader set of memory devices and a broader set of acceleration devices to get tied to. So how do we do this? We were looking at what we had before. So historically, we'd built accelerators using a PCIe ecosystem. And so we started back in Power 8 with doing coherent accelerators on PCIe. But the problem we ran into is the latency of a PCIe stack was much higher than we needed, right? I just said 700 nanoseconds to talk to PCIe, which is just tremendously too long. So we also needed to have a way to do coherence. PCIe doesn't have a typically good coherent mechanism in it. And to do things involving coherence, you need virtual channels. Those are expensive in PCIe ecosystems. You also need different types of formatting and templating. So we started with a clean sheet design that we based around our previous work in attaching low latency memory devices and also the previous work we did in accelerators to build this device where you could have a very thin layer in the accelerator that would talk across an open interface with low latency. We had to go clean sheet, though, because if you looked at the way the PCIe packets were made, the way they were encoded, that was sort of incompatible with what we wanted to build. The one interesting point, though, just a side note, is the electrical standard with PCIe is actually fairly reasonable. It's a differential signaling interface. It runs at fairly high frequencies. And we've found that the electrical signaling with PCIe is actually quite compatible with OpenCAPI. So a lot of the vendors we've talked to currently have a PCIe-based NIC, whatnot, are able to take that same I/O interface that talks PCIe and have it run higher frequency and then talk OpenCAPI. So electrically, PCIe is pretty good. The problem we had with it really was how are the packets formatted and how are those packets aligned? And a little low frequency. But if we bump the frequency up, reorganize the way the packets work, quite a bit of an improvement can be made. That said, so that's how we create the OpenCAPI bus, open standard. So addressing, this is an interesting discussion, especially when you talk about how you do virtualization and integrate accelerators into your work. So what we want the accelerator to see is just what a processor sees, which is an effective address or a virtual address. So when you dereference a pointer in your program, that the actual physical location has been hidden from the application. Those pointers run in a true virtual memory system, so if I want to dereference a pointer, it might be on disk, it might be paged in memory, it may not be paged in memory, but it's just a pointer. So we want the accelerators to be able to operate using those same virtual addresses that the processors need. Now today, with an I/O type of infrastructure, you often need to make calls to the I/O MMU to set up translations for the I/O device, and those pages need to be pinned. And so the software overhead to go give a block of data to a DMA engine is quite prohibitive. So we want to be able to have the processor use the same page tables as the accelerator. To do that, though, we need to be able to handle I/O and validations, translation and validations, and all these things. So that's a big part of what we're building in the OpenCAPI protocol, is a way to have all those things be straight virtual addressing. And what we do is we actually do translation from the virtual address to the physical address in the host bridge. So from an accelerator's perspective, all it sees is program addresses. We hide what the actual physical address is from the accelerator, and that enables security. It enables really simplified translation shootdowns and a variety of things. But that's a big part of the programming model, right, which is we want a CPU that's executing code. We want an accelerator that's operating on those same shared data structures. We want those all to be tied to this same sort of flat memory space, right? So processor going to system memory, accelerator going to system memory, looks the same. We also need to integrate device memory into that same flat address space, right? So if you're writing code and you want to target an operation into device memory, you want to target it into system memory, those should look the same to the programmer. So we need to provide flat virtual address space and able to integrate device memory into the same system map as the memory. So this is kind of how we see this heterogeneous world working. You can also think about multiple kinds of memory. There could be DRAM-based memory in the system. There could be phase change memory, any variety of different memory devices. All need to map into the same shared address space. So this one I guess I have a little bit of passion about in memory in systems. So the way we attach memory historically in like a typical industry system is with DDR memory. And direct attached DDR memory is really a horrible interface. It runs at low frequency, right? If I'm talking about DDR, it's running maybe at 2500, 2.6 gigahertz. This is an extremely low frequency compared to what we give differential signaling. In the differential space, we're at 25 gig today. So we're running like 10 times faster device to processor interfaces compared to DDR. The other problem with DDR is it's not very scalable. As we try and put more memory devices on this bidirectional bus has more loads, it runs at lower frequency. The DDR interface is also it doesn't hide the memory device from the processor. So if I put DDR4 memory on a processor, that has a very specific electrical standard timing interface. If I want to go plug DDR5 memory into a processor, I have to have a totally different electrical standard. So there's incompatibilities. And what if I want to plug phase change memory into that processor slot? Now I have to come up with some, I'm going to call it slightly hacky approach to try and integrate different memory latencies into this very, bare DDR protocol. And so the DDR protocol has big problems. It's too slow, and it's too tied to the device media. And so what we need to do is we want to run it on differential signaling, just like every other interface in the processor is moved to other than memory. So what does differential signaling gives you? It gives you a massive increase in bandwidth. And it also enables you to develop a protocol that's memory agnostic. So I do a load out to memory, and when the data comes back, it might be an out of order, it might be at variable latency. It comes back, and I didn't care whether or not it was DDR4, phase change memory, graphics memory. The load went out to the network, right? So attaching memory with differential signaling is tremendously the right way to go. And what we've done here is we basically have made a variety of memory form factors. This connector you'll see later in a little bit, as are the form factors. But we built a buffer chip. You can think of this as equivalent to like an LR buffer chip, but instead of talking DDR out one side, it talks, differential signaling. Then it talks to DRAM devices, and we have different varieties of these. We have short ones to fit in little 1U servers. We have tall ones, which have higher RAS or redundancy features. It could be phase change memory, storage class memory. It could be any variety of things. But one thing we've done, and this is something that you'll see that's a little different from the next presentation, is we've optimized this for extreme low latency. And by extreme low latency, we have about a 5 nanosecond delta between using direct attached memory or this SerDes-based memory. And that's accomplished with a lot of tricks in the protocol that we've developed on previous buffered solutions. Right? And that's a significant difference from other protocols. Now that said, that means the protocols themselves are very much associated with a direct host attachment. Right? We don't have switching capability in OpenCAPI. This is, I can plug a DDR memory in with minimal latency add, right, in the idle case. So 5 nanoseconds in the idle case turns into a positive latency in the loaded case, right, because I'm able to put that much more memory behind my processor. So this is pretty important with what we're doing here and a big step at what's differentiating future IBM systems. And we really like to get the rest of the ecosystem to pick up on this device because it really is a way to build better memory subsystems. So what are the different types of paradigms we see? We kind of already talked about this, but we want to be able to do direct DDR replacement. So instead of having DDR DIMMs, we'd like to plug in those other DIMMs, memory DIMMs you saw there. Those enable this to be a generic agnostic interface. So that same processor, I can now plug in storage class memory. Storage class memory with different memory latencies, different ordering rules. One other thing I should mention about storage class memory and this interface is that writes in this OpenCAPI interface are explicitly acknowledged. Right? So when you send the write to the device can then acknowledge when that write completed. This can then be tied into your I/O libraries on your processor, right? Because that's typically how this persistent works, is you do a write, a store rather, you execute some flush operations. When those flush operations complete, then you know the data is secure. But with traditional DDR interfaces, and this is especially true in some of these flashback devices, you do a write to DDR, and it just says, OK, yeah, there's no acknowledge, right? There's nothing in the DDR protocol that enables you to say, this is when my write's secure. There's no explicit acknowledge. It's just you send the data, and if there wasn't an error, life is good. The problem is you don't know if it really got there or not. And so since we have an explicit write acknowledge, that enables much more sophisticated persistence mechanisms in the memory. And there's nothing to say that the OpenCAPI devices couldn't have tiering. And so we've looked at some devices where one processor interface talks to DDR as sort of a cache of memory that lives behind it. Right? So you could tier things. You could also bridge to other memory technologies here. Right? You could come out the back of this. You could have a Gen Z connector just to try and talk about things. Right? So you've got your low latency connectivity to your DDR. And then you could have the back of that go off talk to other memory standards. Right? So that's kind of how we see that. This is a little bit of a rehash of what we already saw, but we have host processors, we have accelerated processors, we have accelerator memory. This could be HBM in the case of like a GPU. We have host memory, which is, and this is all shared. We can issue atomic operations. Those are supported on these protocols. Different threads can all communicate sort of in one happy family. Accelerators, and this is kind of interesting, is that memory devices, as they become more sophisticated, want to be more than just slaves. Right? If I have a device that maybe is doing compression or is mixing, it wants to be a memory slave some of the time, but it also wants to master operations. Right? I think we saw some of the earlier presentations where you put a device memory out there, maybe it has the ability to compress and decompress data as it goes. But to do so, maybe it needs to talk to the processor to learn encryption keys. Maybe it needs to figure out what decompression dictionary needs to be used. And so you get this hybrid approach where you have a memory device where it looks like loads and stores, but it's sort of a smart memory device. It needs to be able to initiate accelerated operations, right? It needs to master commands. And so that's another thing you don't get with a DDR interface, is you don't get the ability to have the accelerator generate an interrupt. It can't issue a load. It can't be its own master. And so the nice part here that we merged sort of the OpenCAPI memory interface with the OpenCAPI accelerator interface is that it can be an accelerator and a memory device at the same time. And a lot of times the accelerator devices have memory behind them. And so this enables a wide variety of paradigms on, what is my accelerator doing? Maybe I'm doing just simple offload where I go tell it to do work, it does the work. But potentially it's sitting on the network, right, which enables it to do compression, decompression, encryption. It may have its own memory on the device. If it has its own memory on the device, it's maybe accessing that concurrently with the other processor. So these are the kind of devices we really want to build in these new emerging spaces. Signaling technology here, I'm just a little comment here. Right now we're at 25 gig, which is what our processors today support. We have a roadmap going out to about 2021 currently, which shows us going 32 gig, 56 gig are the type of frequencies we're looking at doing in that 21 kind of time frame. The other thing that's important is the standard here is this is a fairly easy to digest memory standard. It matches Xilinx FPGAs, SerDes. We haven't come across a single vendor yet who can't support this differential signaling technology. It also has a lot in common with the next presenter. It's common with them. The other thing to mention here is we do have work groups to help defining these things. One of those things we use in the work group is a common 25 gig signaling. We use this signaling for SMP Interconnect. We also use this same signaling standard for our NVIDIA NVLink attach. So same 25 gig, we actually have currently 3 personalities on our processors. We can talk OpenCAPI across those links. We can talk NVIDIA NVLink, and we also use the same protocol for our processor interconnect. And this is kind of an interesting thing in that the silicon area is mostly dedicated to the SerDes signaling estimate. The actual thing that decodes what a translation block looks like is pretty tiny. And so far we've been successful with we have 3 technologies on this protocol, and it's really quite tenable. It's not a significant tax on our processor chip. So let's kind of look at what a OpenCAPI system looks like if we think about our future. We have a derivative Power 9 system that will look just like this. And what is that? Nearly all of my signal IOs, or ideally all of the signal IOs coming off the processor, are this differential signaling. And that lets us build a very composable system where maybe somebody wants to build a system with just lots of DDR bandwidth, right? Some HPC lab, they got a bunch of codes, they care only about memory bandwidth, they dedicated all these 25 gig signaling things for memory, and they have a terabyte per second of memory bandwidth, right? Per socket, right? 10x factor over what you can do today approximately. That makes their codes run 8x faster. Big TCO win for those organizations. Let's say you want to run a database that wants lots of persistent memory, right? So you dedicate half of these IOs to persistent memory, half of them for DDR, right? Depending on what exact ratio you need. It lets you build exactly what you want. You can use some of these lanes for accelerators, right? So it lets us take one processor chip, one host silicon, and then compose, picking up different accelerators, different memory, and tie them all together, right? So that's what we like a lot as CPU designers about these sort of universal interfaces, is it lets us build a variety of optimized systems with different components to them. This is all tied together with the things we just talked about. A little bit of roadmap here. OpenCAPI is kind of an interesting name. CAPI was the name we used for our proprietary accelerator attach going back to Power 8, which was tunneling these coherent operations across PCIe. That we saw the latency was kind of painful. We really needed to get better latency. That's why we transitioned to the direct 25 gig signaling. We made it open as well because the particular thing we had with CAPI was a little complex, and we needed to move IP from the accelerator to the host. So we made our host do more work, the accelerator do less work, and then we made it open. And that's what we have today, Power 9. We've been shipping these for not quite a year, but close to a year, and that has 25 gig accelerator interface. For a Power 9 follow-on, we will extend our OpenCAPI capability, and we'll add this low latency memory interface. The Power 9 you see here, for its memory, we have two versions. One of them is just traditional DDR. The other one is our proprietary buffered memory solution. So that same technology in our proprietary buffered one is what we've put into the OpenCAPI standard, which is what this 3.0 version is, and that's what we'll have our next chip here. But memory bandwidth-wise, we're talking a standard DDR4 memory subsystem based around OpenCAPI. We have like 450, 400 gigabytes per second of sustained bandwidth. So a massive bump in bandwidth to support accelerators, high-performance computing, so big bump in bandwidth. And this is something where we'd like to see other vendors pick this up, right? Or even accelerators, right? If you want to put a lot of memory behind an accelerator, use this OpenCAPI memory interface. So that's what we have on the short list. Talk a little bit about what these things look like. We found that running this high-frequency interface, we typically want to do through cabling solutions. The motherboard, if you're going to run 25, 32, 50 gig, the material becomes more expensive. And so we're actually kind of trying to border between, do you want to do all cabled solutions, right? That way your motherboard can just be power and ground. We could take these cables off the top of a module, perhaps, and have them go directly to accelerators. So today we're pretty centric around cables. We have a short reach in the motherboard from the processor socket. Then we have these jumper cables that can go plug into the card. To make this sort of simple, the first prototype cards we did, we put them on a PCIe bus. We get power and ground from the PCIe bus. We plug it into the box. We run one of these jumper cables to run the 25 gig over. So what do some of these parts look like? This is an FPGA card from Alpha Data. This particular one had the connector on the side. Production versions of this have the connector at the back. But essentially, it looks just like a PCIe card, except it has this 8 lanes of 25 gig going into the side of it. And this is kind of an interesting card that Mellanox has built, which is a hybrid device. And so it takes their standard NIC, which continues to use the PCIe bus, but then it has a parallel FPGA on the card that talks OpenCAPI. So you kind of think about this as you're able to take your NIC where the data flows to the NIC, and the NIC can either route commands to the processor, but it also can route commands directly to an FPGA. And that FPGA you can think of as an extension of the processor, right? It's tightly coupled coherently with the CPU, and this enables it to run packet inspection things as if you had a little algorithm moved onto the card. So this does show kind of how you can sort of hybridize different devices. This has InfiniBand Ethernet merged with OpenCAPI, right? So different networking solutions can merge with OpenCAPI to sort of build these devices together. Just to comment, the 25 gig stuff runs clean. There's no reason it shouldn't. It's a fairly standard interface. But yeah, we do have these in the lab. There's probably actually about 4 different FPGA card variants that are OpenCAPI cards that people can buy. So we have a consortium for OpenCAPI. The president, are you still the president, Myron? Yes. Raise your hand. There's the president. Elected, yeah. Anyway, try not to talk about that. All right, so we have, we're trying to proliferate this, working to get members to help build accelerators and adopt the standard. And you can join today. There's different membership levels, like many of these consortiums. And feel free to talk to Myron about it. So that's what I have. And now we're going to switch to our next presenter. Thanks.
Thanks, Jeff. We're just going to roll right into the second part, Gen Z. To do that, that's Curtis Bowman. He's president of the Gen Z Consortium, as well as director of technology and architecture in Dell's server CTO office. His areas of interest are converged and hyper-converged systems, accelerators for HPC, machine learning, data analytics, 25 years of experience in architecture development and business justification of server storage, commercial and consumer products. Thank you.
Well, thank you, and let me get this. Good to see everybody here today. Unfortunately, I don't have any good jokes to start off with, like Jeff did. So, I find myself in the same boat that Austin was in yesterday, where I know I'm between you and lunch. So I will try and get through this. And then don't forget, we've got the question section at the end. So as you got questions, we'll get Jeff back up here, and you can ask both of us some questions. The disclaimer that you've seen otherwise, you know, it says, hey, I'm going to lie to you while I'm up here because I can't predict the future as well as I'm going to act like I can. But let me start off with just a little bit about the consortium. So Gen Z is fairly new. We were founded 2 years ago this month, and we started with a 12-member team. Now we're up to over 60 companies that are with us, and we've been able to show some really great demos. If you've been to Supercomputer Flash Memory Summit, you've had a chance maybe to see our demos, but essentially it allows us to show servers connected to pools of memory and then running right out of that pool of memory. So we can actually execute code out of the memory pools. And then we've got a lot of stuff going on. People like PLDA and IntelliProp have both got IP that's available for us. The good folks at Microsemi are starting to do some work on some silicon that will be available in the 2020 timeframe. And we also have some devices that I'll talk about a little later in the presentation from folks like Smart Modular. And then finally, the big thing that we pride ourselves on is we're completely open. So if you go out to our website, you're going to find our latest specs are all posted out there. There's no challenge to get to them. And we also put a lot of our draft specs out there for you to look at. And then we encourage feedback. We'd love to get your feedback. If you see something that seems like it's missing or something that's not there, we've got a feedback form that you can give us the feedback right away. And that helps to make sure that even if you can't become a member, that you're available to give us the input that we're looking for. To give you an idea of who our members are, and I'm not going to read off the whole list, but you can kind of see the 60-ish members that are there. The big thing we want to show here is we have everything needed for an ecosystem. So you see the CPU vendors, you see the silicon vendors, you see the software vendors, the connector vendors, and a number of OEMs that can put the products out. Right, so that we're really ready to put something new on. And what this has done is allowed us to move fairly quickly. So you're going to see, if you go out to our website, a number of specs that we've posted around the spec for the architecture itself, as well as a number of mechanical and PHY specs, because we've done those with a great group of people that have helped us out. If you see your name up there, thank you very much. We appreciate your help. If you don't see your name up there, hint Amber, we'd love to have you join. Because we think that we're really moving along in an area that the industry is going to need this kind of help. Why do we need Gen Z? That's always the question we get. So it starts off with cores are growing at an exponential rate. So anybody who's designed with a CPU recently realizes, hey, I got a ton of cores. The problem is pin count limits what else can be done on that CPU. And so when you start to look at the memory channels, they really haven't grown significantly, right? We had 4, we've moved to 6 or 8 depending on the vendor. And then we're kind of stuck there because 4,000 pins is already a huge aircraft carrier of a device. We also have limited ourselves in PCIe lanes. We're anywhere from 48 to 84 PCIe lanes. So our I/O bandwidth isn't really growing either. And so when you look at what that does per core, you see that both of them are negative trends, which means it's harder and harder to get things in and out of the CPU. And we want to be able to change that. And we think Gen Z is a way to go do that. The other things that makes it important, and we've had lots of conversations, Dave had a great look at what storage class memories are out there and available, so I won't jump into that too much. But it's that space between DRAM and SSDs that really is looking for an answer, right? And it's 3 orders of magnitude difference. So Intel has done a great job with a 3D XPoint of starting to come into this space. But one thing you look at is you see here, storage class memory is byte addressable. And so it's very much like memory. But the other piece that's not very much like memory is it's persistent. And so anybody who's done storage systems for any time knows persistence brings a whole new paradigm to what you need to think about when you're talking to that memory. It can't just go away because a VR failed somewhere. If it does, my availability goes away, and I'm no longer useful to the customer. I need to start thinking of memory very much like I think of storage. It's about availability, not reliability. It's about serviceability and how I get to it. Anybody who's tried to replace a DIMM realizes, right, I got to get my strap out, I got to get in and pull something out delicately and put a new piece in. That doesn't work, right? And the storage guys have known it forever. That's why you've got U.2, to just plug something in and make it easy to replace something that's failed. The other thing is, you look at the bottom of the slide, is this is kind of what we see going forward. Right now today, we have DRAM, and we have a good set of spinning or solid state disks. Storage class memory starts to come in with 3D XPoint and some of the other things that you saw today. And over time, actually is the winner in the space. Right? So it's going to push the flash down to colder and colder areas, and it's going to be pushing memory up into just exactly what I need. I don't want to spend a lot more on memory. So as we looked at Gen Z, we said, what do we need? Well, obviously we need high performance. So high performance comes in simple, right? High bandwidth, low latency solutions. We also need something that avoids protocol translations. We don't want to jump between protocols because it just wastes time and energy. It also has to have low software complexity. I don't want a large stack that I have to run through. You kind of saw on some of Amber's slides how much that takes away from your performance because you're running through the software stack. It needs to be highly reliable. No single point of failure. It needs to have multipath. Again, you can't let persistent memory disappear on you for no reason. Security. Everybody today, and that's a big thing that's in almost every news article, is somehow security has come in. So with Gen Z being defined just recently, it thinks about security at a different level than some of the buses that have been defined 10 or 20 years ago. And so we have the ability to look at the device, and if it doesn't have the right keys, the packet itself may never get through the switch to get down to your device. So it may never see errant code or malicious code trying to modify your memory. Flexibility is important to us, of course. So you need to be able to support multiple topologies. In fact, as you look here, you kind of see this is the standard look where you have all your devices connected in through a CPU. What we want to do is we want to get accelerators pushed out into pools. We want to get memory pushed out into pools and be able to have storage and I/O also in those pools. So that I now can compose systems rather than have to think about buying everything at one time. And we'll get into that a little later in the presentation. Compatibility is important to us because we need to be able to use what's there today. In fact, PCIe or PCI to PCIe transition is what inspired this. If you think about when we went to PCIe, really all you had to do was have PCI ready software, and it worked immediately on PCIe. Over time, the OSs and the applications started to take advantage of what PCIe brought. So we're doing the same thing. You don't need to have any new OSs. You don't have to have modified applications to be able to use Gen Z in the solution that we're looking at here. And then, of course, it needs to have an economic advantage or people won't pick up on it. All right, there we go. So then all you do is you put Gen Z in as a fabric. It has multipath so that if you have a failure in one path, you can go to another path. And it allows you to put things like your DRAM or your storage class memory as well as your other devices out on this fabric. And they can be inside the box or they can be outside the box. Let me give you a quick example of just memory. So if you think about the processors that we have today, we've got an MMU, and Jeff actually talked nicely about that. We want to be behind the MMU, not the IOMMU. So you have your standard connection to DRAM. What we do is we just put the Gen Z protocol engine in here, and now we can talk to our memory directly, including storage class memory. And you'll notice now I have dual paths to them. So I can support that multiple path need that I have. You also find that this memory connection, if you think about it, what we're doing, we support both PCIe and 802.3 PHYs or Ethernet PHYs. So when you go to that, you start to see, as simple as 16 gigatransfers per second like we have in today's PCIe, all the way up to 112 gigatransfers per second, which is the next generation Ethernet. All those PHYs work through there. And what that does is give you a per channel bandwidth of up to 400 gigatransfers or gigabytes per second. Put that in perspective, that's 8 DDR5 channels. that you can put out on the end of one Gen Z link. And then kind of going through the rest of it, we support the point-to-point as well as switch-based topologies. So if you're trying to go inside the box, you can go point-to-point. If you want to go out onto the network or a fabric, you can exit the box. This is what Jeff already said you were going to see. Here's the connector. So this is the connector that we worked with Tyco with, called the sliver connector. And you can see it has multiple, what we call chiclets. 1 chiclet, 2 chiclets, or 4 chiclets. It's just a simple 8, 16, or 32 lanes. If you liken that to PCIe, that's the by 4, the by 8, and the by 16. The difference is the bandwidth. You can see on a by 16 starts at 100 gigabytes per second, going up to the 448 gigabytes per second I was talking about. Even on just 8 lanes, it can be up to, or start at 25 and continue up from there to 112. There's also a host of different types, so we can go right to the cable. That's what we were talking about. It'll help you limit your expenses, right? If you go to some really low loss material on your PCB, you're going to have a large expense, especially on a big server-sized PCB. So instead, get off to a cable, get off to some optics, look at your right angle or board-to-board style connectors in that same space. We've also done quite a bit of work on form factor. So we have the single wide and the double wide form factors that allow you to plug in, and working with our partners that are in the memory areas, what we found is on the SSDs, we can get up to 48 terabytes in a unit. For storage class memory, the prediction here working with those is about 5 terabytes in a single unit. And then DRAM, we can get up to 280 terabytes. That form factor is what Smart Modular showed off at Flash Memory Summit as a 96 gig device just a month ago. So we're starting to see these come into the marketplace. You can also see that we looked forward, considering what other types of devices we wanted to connect into Gen Z, and so we've got GPUs that can be connected in, FPGAs. Obviously, those would be able to fit things like smart NICs and other storage devices. One thing I should have mentioned there is, I'll go back to it just real quick. If you look at the connector, we have something that's unique in the connector. I can take obviously a little 1C device and I can stick it into a 4C socket. But this connector actually allows you to take the 4C device and stick it into a 1C socket. There's nothing that prevents you from using any of the devices in any of the connectors, because they all have the same keying that goes on. So if I don't have the perfect slot for my device, it's okay, because I can add that in anyway. Then what does that give us? That looks like something where we have a nice enclosure. We actually go out and you start to think about, see if I can go back, something that has a drawer full of devices. So I can take a drawer and I can add a couple of memory modules, I can add a CPU, I can add a GPU, and maybe an FPGA, plug it all in, and now I've got a nice little system, right? And as I add more drawers, I can add more components and either add them to the current system or start to make a new system. And so as we get into what does it mean to be composable, Gen Z allows that composability at rack scale. Now let's talk a little bit about the OS stuff. I said, hey, you don't need a modified OS. And that's because as you look at what we're doing, we've got a standard NVMe driver that we can use with just very minor modifications that we've been able to now make it so you can talk to the Gen Z hardware. So if you want to put just standard SSDs out there or NVMe drives, it's available to you. If you wanted to talk to memory, you can do it one of two ways. You can talk to it as a memory device with just load store, or you can talk to it as a block device using that same driver. And then finally, we do messaging. And you can do messaging in one or two ways. The easiest way that we've put together is essentially like you see in a hypervisor. You get a virtual NIC or an eNIC, and you're able to use that to message to your other devices. Simple messaging can be used to tell another device out on the end of the bus, hey, I've got data ready for you. Here's where it's at. Let's go use that data. And let that device pull the data to itself, right? So you're not using the CPU cycles to do a lot of data movement. The other would be to do an OFI type device where you actually, for something like HPC now, you have a very fast, about 250 nanosecond messaging opportunity. Composable memory is one of the things that we all talk about, but today we don't know how to do that, right? The current buses, whether it's PCIe or Ethernet, InfiniBand, all of those don't really allow you to run at the speed of memory. And so Gen Z, that was the main thing that we wanted to do, was be able to show how memory can get outside the box and allow you to compose that into a system later. If you think about it right now, all memory sits behind a processor of some sort, whether that's a CPU or a GPU. And anybody who wants to get to that memory is really a second-class citizen, right? I can't get to it unless I go through the processor. Also, if something happens to that processor, maybe it goes bad, maybe a VR around it goes bad, all the memory that sits behind it is gone, right? So it doesn't really meet that high availability model that we need in memory. On the Gen Z side of things, we allow multiple different ways to connect up. So you can do a mesh, you can do a simple direct connect, and you can also do a fabric. And so you can connect to these different devices, and everybody is a first-class citizen. If a GPU wants to hit a section of memory, it can do that. And this memory can be assigned either directly, so allocated, or it can be shared and allow for multiple devices to talk into that same memory space. We also support PCIe devices in a simple thing called logical PCIe device. What it does is when it's a Gen Z looking piece, what you see here is nice native Gen Z looking through a switch. That switch has a 30 nanosecond cut through time compared to a PCIe switch. And then you look down here at your different SSD, a GPU, whatever you have. And so you're saving about 200 to 240 nanoseconds round trip time by just using Gen Z. You can also do things like multipathing so that if you lose one of your links, you still have access to it. From a system point of view that doesn't have the Gen Z understanding, these legacy devices are still there. They look just like a standard PCIe device. And you access them by doing memory writes to essentially the space that's down here that looks like your standard PCIe register set. And so you're communicating with them at very low latency, very low CPU overhead. What that means is you start to think about a composable system. Now you're able to do things like pick my CPUs, pick my storage class memory, my SSDs, maybe even a gateway to a bigger storage system, get my data services like RAID and other things put together, composed as an individual storage box. What that does for us when you start to think about it at a server level is now I have these pools of resources, right? And when I want to take and make something out of it, I start to add a rack scale fabric and a server builder, for lack of a better term, right? A management piece that actually goes out and discovers the devices and allows you to put them together. Then I start to build a system. And I can bring my, just the right amount of CPUs in, just the right amount of DRAM, storage class memory, et cetera, all go into the system. Now I'm ready to load my application on top of this, and it looks like just a standard server. Now, there's nothing about it you can't do just like you do with a server you might put into a rack that's a 1U or 2U server. So nice bare metal server, I load my application on top of it, and now I'm ready to start building my next server that has different characteristics. So the next server needs a lot more storage than the previous one. I build those in. If I'm wrong, I can always add more later. Or if I'm wrong, I can take something back and reallocate it to the pool. So one of the things you heard about yesterday was, hey, let's quit buying all this over-provisioned stuff. It allows you to put your over-provisioning just into the pool. So instead of the 60% I think that was being talked about yesterday per server, you can over-provision your pool slightly by maybe 20%. And then if you need to, you buy just what you need. You don't end up buying a little bit of everything to get that piece that you need. If you look at an ideal state, and it looks like my fonts didn't come through well, but I can have compute, I can have a nice Gen Z type of a fabric here. I can go to something that is memory, maybe some SCM, some SSDs, and then some standard hard drives down here as a rack. When I go to put it together, I actually am looking at it as, what's my application that I want to run? It's not what hardware did I have to buy, it's what application did I want to run and what does it require. So you can look at, hey, I can now, my in-memory database had a need, I can do some some software-defined storage. And so if you look at the advantages, the customer gets the capitalization of pay-as-you-go. For the end users, I get to adjust it for what I need. And for IT folks, it really allows you to orchestrate the business and become very efficient. So the benefits, compose things, then go off, get those resources untrapped. So make it so that if I lose a piece, it's not a big deal. I can just reallocate something new. Avoid the over-provisioning, purchase the resources when needed, increase your reliability, availability, serviceability, repurpose the old stuff, right? When I don't need it anymore, that's great, put it back in the pool and use it for my next server needs. And then allow things to move at the speed of that particular technology. Didn't hit on this a lot, but if I go to Gen Z, I put the memory controller out with the memory, or the media controller rather, out with the memory device. So I don't have to wait for a CPU spin just because I want to go to the next best memory. And you saw in Dave's presentation a number of memories that are coming down. And though some of them were in the dream sequence, right? There's a lot of people working on different types of storage class memory. They're going to be coming down and they're not going to be aligned with a CPU cycle. So you need something to abstract you from that CPU cycle to this, and so we think Gen Z is a great way to abstract yourself. Finally, with a little bit of work that we've been doing and some modeling that we've been doing, we see some great opportunities for performance boosts. The Spark, 15–20% faster because it's just modifying existing frameworks, and we actually have that Spark work out today. If you start to think about the new algorithms you can do, because now I can really put things together in the way I want to do them, I can start to see 100x increase. And if you actually go brand new rethink of what I'm going to do, we believe that you can see things like in the financial world where you get about an 8,000 times speed up of what we're doing. So with that, I think we now move into the question and answer session, but I would encourage you to ask some great questions and join Gen Z.
Thank you, Curtis.
Yeah, come back up.
Thank you, Curtis. While we assemble the speakers, we're going to enter the discussion part of this. We're going to have a microphone that moves around for questions, okay? We're recording, and that'll make a better fidelity for the recording and everything else. And so I just want to kick it off while we get that going and ask our speakers, thanks for not food fighting. It's great. I love it. You actually showed some hints at how these things might dovetail, but maybe you could open the discussion by actually telling us some ideas about how these things will work together in a complementary way as we go forward.
You want to go first?
Yeah, I think I covered on this, right? I mean, the key thing, so if I look at the differences, let me try and highlight this. Mm-hmm. OpenCAPI is very centric with having very low latency and tightly coupled coherence between a host silicon and the accelerators. I feel like Gen Z, while you say you can be host memory, mm-hmm. I think from a latency perspective, we're much lower latency, but we have nothing in OpenCAPI associated with switches, partially because the optimizations we have to achieve low latency and some of this coherence things aren't tenable in switches.
Right.
So how do they go together?
I agree. You saw on the one chart with the pyramids, we don't see standard memory going away from attaching to the CPU. And that's something that OpenCAPI brings, a great attach to the CPU. What we see is a tiering of memory that needs to occur. much like we see in tiering of storage. And so as you go from something that might be integrated into the host to something connected directly to the host, we think the next step is something that goes across Gen Z. We don't have the same latencies, right? You talked about your latencies or the latencies of a DDR type of a channel. Gen Z is larger than those, so we're not in trying to replace those, and I think that's where we dovetail quite nicely in an opportunity to have directly connected memory and then have larger, less expensive pools of memory that you can use, as I showed in some of my later slides.
Thank you. Where'd the mic go? Oh, it looks like
I've
it's
got
been
the mic.
distributed already.
Hi, everyone. I'm Steve Bates from Adedicom. So can you guys comment a little on the operating support that's going to be needed to make all of this work? I just had a look in kernel.org, and I see a driver for OpenCAPI, which is great. But Curtis, to your point, right, you're envisioning a world where I have a processor running Linux, and Gen Z is going to arrive and basically create maybe 4 or 8 or 16 terabytes of new memory inside the operating system. That the operating system also now has to be cognizant that some of this is memory that I can put into my slab allocator. Some of it's memory, but it's kind of slow, and it's also persistent. So I can't put that on my slab allocator. I got to do something maybe DAX-ish with it. And some of that memory is memory mapped accelerators that I better not do load storage against because it'll actually make an FPGA do something. And then you had a slide that said there's no OS changes. Like, I can't reconcile that. Like, I can't. So can you maybe comment on that?
Yeah, absolutely. So Gen Z maps into the standard memory map of the processor, right? So
that crashes most OSs today. You insert a whole bunch of memory. It works on an Intel. It doesn't work on ARM. And it doesn't work on RISC-V. And it doesn't work on pretty much anything except AMD 64.
So our earlier focus has been on some of the AMD stuff, some of the Cavium as members, ARM. So there are limitations to memory space there. So you'd have to be cognizant of those limitations early. But again, if you're looking for a reasonable amount of memory, then you can use Gen Z to attach to that. As you're going to bigger and bigger memory areas, then yes, we're going to have to continue to work with the ARM folks and some of the other processor guys to allow for those large memory spaces to occur.
I guess I'm just asking, can you go talk to the Linux community and start getting them intrigued and starting to help point out where hotspots and the problems are going to be inside the Linux kernel? Because I think it would behoove you as an organization to do that ASAP.
Great input. Yes, and as you might have noticed, Red Hat is actually a member. And so those discussions are going on, but I'm not sure it's out into the wild yet.
Yeah, I mean, I think any of the software sides of different types of memory it's an emerging, right? And so Linux's capability to understand different types of memory, it sort of has to happen. And you see it in, whether or not you're doing the Intel, plug it into a DIMM slot, or whether or not it's an OpenCAPI slot. The software looks kind of similar. It's got to be cognizant of all the different types of memory and understand how to do that. That's a big software challenge, but it's not really tied necessarily to the protocol.
No.
We need DIMMs to say, I am a storage class memory DIMM with this kind of access parameter. And then, is that NFIT? Is that JEDEC? And then the OSs have to know how to talk to that interface to go, okay, so you're giving me 7 terabytes, but it's not DRAM-like, it's more like something with this kind of access, and I got to work out what to do.
Yeah, I mean, think about the tiering. As you get high bandwidth memory or HBM 1, 2 into processors, that's going to be one tier that's very fast, low latency, but not very big. You're going to have standard attached DRAM that is another class. You're going to have storage class memory that's yet another class. I'm not sure that Gen Z in and of itself is the only one who's going to have to deal with that problem, but we're having those conversations. That's going to be a problem that the world has. It needs to identify itself in speed and whether or not it's persistent. And so, yes, those are being worked, and JEDEC is one place to do that, and they're working actually with the PMEM initiative on coming up with some of those pieces as well. We're going to give you your exercise.
Thanks, Lucy.
I noticed both OpenCAPI and Gen Z have FPGAs to let people play around with this stuff. NVIDIA seems to be a member of OpenCAPI, but not Gen Z or C6. Do you guys have any thoughts about why GPU accelerators, which are very common in data centers, AWS and Azure data centers, are showing up, but it doesn't seem to be a point of focus for either OpenCAPI or Gen Z?
You got him as a member. I'll let you take that
Yeah,
one.
I don't think I can really speak for NVIDIA, as I'm an IBM employee and not a NVIDIA employee. So yeah, I don't think I can say much about why they're in one or the other. I'm not quite sure I got the rest of the question.
Oh, accelerators. How come there aren't any NVIDIA or GPU accelerators you can play with? AMD or?
Oh, for OpenCAPI?
Yeah.
Yeah, I think it's partially a point in time, right? We had NVLink attach before we had OpenCAPI attach.
Yeah.
And so that enables
These things are just 2 years old, remember. I mean.
Well, you know, as you look at the partners we have, AMD is part of Gen Z, and that's not just the processor side. So they are looking at this, but you know, Tom brings up a very good point. We're young, we have to prove ourselves, and right now, GPU folks have a lot of other things they're focused on.
Yeah, I mean, the first thing is FPGAs, because heck, those are easy. And then memory is probably the next easiest one, and then accelerators are, you know, probably the order.
In Gen Z, you are introducing all these devices under MMU. So the question, doesn't it introduce also a new category of problems, especially with error handling, with some stalling CPU cores? So how it is to be solved?
Yes, yes, it does. You know, when you start to put more and more things behind the MMU, if you get a problem, you start to stall cores. And so we are looking into the management of that, and how do you work through it, and are there changes that would need to be made in the MMU to allow for this, and some, you know, how do you maybe split transactions and other things so you don't stall the core.
Thank you. And the second small question, so you also said that you are able to emulate legacy PCI devices with Gen Z. So what about, for example, interrupt handling when you are under MMU?
When you're under what?
With interrupts. So do you have an idea to support interrupts?
Yes. So, you know, essentially you're just tunneling PCIe across Gen Z, and so it looks very much like a standard PCIe interface to the host.
Okay, thank you.
But we're not really used to MMU attached devices passing interrupts, I think was part of that question.
Yes.
So it is an interesting confluence, I/O and memory.
It is, and yet we think that it really is not going to be used for everything, right? But for things where you're looking for low latency accesses to PCIe devices, that's where it's helpful. That's where we were showing kind of the GPUs and the
Exactly.
NVMe devices is the real candidates for that.
So yeah. Oh, sorry. I mean, we have interrupts in OpenCAPI. They're address mapped. It kind of looks like a special magic address.
So you can then trigger some I/O action just when device is under MMU, right?
Well, this is maybe a hard conversation to have, but yeah, I mean, there's interrupt support. You do have some interesting things where if you have a page fault, like an I/O device typically would have never had a page fault in the past. Yeah, right. But that is a new thing maybe devices have to deal with.
So in Gen Z, you said processor is always going to have its own memory. And so we have two classes of memory. One is slower memory over the Gen Z, right? So I'm assuming the instructions will always be in the direct memory to the processor, and the data will be stored in this slower memory.
I don't think that's going to be the case. You know, the memory size is going to continue to be small, and if you're running an important task, absolutely you might want it into that local memory. But if you think about a machine that's virtualized across a wide space, you're going to run out of that local memory perhaps, and then you're going to put things out into the Gen Z attached memory. And you can still run from there, and so it kind of gets back to the question before of, hey, I need to start to be aware of how, what's my priority, so that I go into the fastest memory possible with all the characteristics I'm looking for. Future applications are going to maybe talk to the OS and say things like, persistence is most important to me. Put me in persistent memory and then give me the fastest stuff in that category. That persistent may be all sitting out on Gen Z, but since persistence was more important, your application is going to be put out there. If instead, no, give me the very fastest memory and I just need a little chunk of it, maybe you go into HBM.
Okay. Thank you.
I can tell you that execute in place is a very interesting question with memory. We begin to provision the speed of memory like we traditionally provision storage. And it's quite an interesting question. Is it better to put it on moderate rate memory and execute it that way, or is it better to migrate it to high-speed local memory? And these things blur that, thereby bringing in that question of management.
I mean, from a text perspective, from a code, I mean, some of it might be infrequently executed. Why waste your expensive DRAM on it, right? And the fact that it is addressable lets you can go and infrequently run code, not have to like page it in, right? It can live out in cheaper, higher latency memory, and depending on the access characteristics, that's where you put it. So some code could be local, some code could be remote. It all just works, depends on the access rates, right? So.
Yeah, so I do think that applications are going to get more and more aware, right? But big thing we got to do is get this out there first, and then let the applications come along. I think Amber talked about it, right? Takes a while. We got to get the hardware in place. We got to let the software developers feel like they've got something that's stable. Then they'll start to do their work.
Question: could both of you speak about multi-mastering, either an interest or demonstrated capability? Like, could there be in the Gen Z case? Could you have two CPU instances talk to the same device across the fabric?
Yeah. So I'll start, but I definitely want to. We actually currently have demos that do that. So we take, right now our demo uses a server that's just nothing but a memory device, and then takes 4 other servers, and we allocate memory to each of the servers as separate pieces, and then we've got another space that's shared amongst all 4 servers. And so we can have all of those servers talk into that one shared spot. Right now, it's the last guy to talk gets to put his data in there. We don't have the coherency going yet, but that's one of the pieces we're working on, is the ability to have coherency in that shared space.
Yeah, I'm not sure. I mean, from a, there's a question here, is this under one OS or under multiple OSs is maybe a differentiator. Under one OS, it's just sort of business as usual. Under multiple OSs, that's probably more of what you guys are targeting rather than OpenCAPI.
Question there, I see.
Here we are.
As you see it, what are the major challenges for Gen Z?
Major challenges for Gen Z. Well, let me talk about some of the near-term stuff. Right now, we're doing a lot of work on our management spec. So if you have interest in that, come join us. You see a lot of the work that I kind of say, hey, this is going to occur. It takes a lot of software effort to get that just working. So there's that piece. The other is, how do we get more ubiquitous? So you heard people say, hey, where's NVIDIA in this? We need them to come along for the ride when they're ready. Where's Intel? They're coming along for the ride in some ways and not in others. We'd love to have them join in and see the value here, because let's face it, they're 90-some-odd% of the data center CPUs.
And that was a Gen Z targeted question, so
yes.
I don't have to answer.
Did I see a question over here before or no? Okay, guess not.
All right, well, thank you, everybody. We'll move on.
folks have.
Tangled a lot. Are you wrapped yours
I tried to wrap mine up.